over to you, Phil. Please just share a little bit about who you are and what sort of knowledge you have, really.
Okay, so, well, I guess I'm interested in all these apologetics debates, and I'm interested in science, and I was studying astronomy at University College London, and I did my project in early universe cosmology, and I had some very good cosmologists help me with that, really top guys. But I still had a lot of questions. I mean, I'm not a cosmologist, but just have that sort of basic level of knowledge. But what I have done that I think puts me in a good position to sort of talk about these topics is I've made a series of films with the world's absolute leading cosmologists about competing models for the early universe, what may have happened at the Big Bang. And I've interviewed Alan Guth, who invented inflationary cosmology. Many people may be familiar with the Vilenkin theorem. It's used in apologetics discussions a lot, so they may know that name. Roger Penrose, who is famous, you know, for the Penrose-Hawking singularity theorems. I've interviewed Gabriele Veneziano, who invented string theory. Abai Ashtekar, who invented the rival theory called loop quantum gravity. So a lot of these, you know, I can go on. A lot of these top cosmologists, and we've always put these films out, but also we've had, you know, many hours discussing a lot of the issues that are relevant to the origins of the universe.
Great. So what we wanted to chat about this evening primarily is two things. One is about cosmology, and in particular the Kalam argument, and if we have time, some of the fine-tuning. I am aware, and I'm very grateful for your time, and so, you know, we've got sort of 2 hours. See how far we can get, you know, in those 2 hours. So I guess for everybody, maybe you could state the Kalam and then share your initial thoughts about what objections you might have to that.
Okay. Well, the Kalam comes in different forms, and it has a long history. But the one that's sort of been popular in recent times was revived in 1979 by the Christian theologian William Lane Craig, and it's been copied. I mean, Craig's words have been copied almost word for word by many Muslim apologists. They literally copy and paste what he says. But the argument basically runs something like this. Everything that begins to exist has a cause. The universe began to exist, so therefore the universe must have a cause, and then they make a number of arguments to try and say that cause must be God. So obviously there's a lot, you know, you could make a whole 2-hour discussion as to what is wrong with it. Probably where I think I have the most to contribute, because I think a lot of people don't realize what most cosmologists actually say about this topic. And I think it's been sort of mis-sold to us, shall we say. The first thing to say is that most people think that modern cosmology has a consensus that the universe had a beginning at the Big Bang. And I think that statement is false. I've spoken to a lot of the top cosmologists in the world, and none of them think that. Not the ones I've spoken to anyway. And I think, you know, you're not even surprised when you speak to cosmologists and they tell you, no, we don't know whether the universe had a beginning. There were reasons in 1979. I mean, I think it's true there was a consensus that the universe had a beginning at the Big Bang. But that's no longer the consensus view anymore. And maybe I should sort of go into why that's no longer the consensus, or why. Probably I could start with why it was a consensus, and then why it no longer is. Is that how you'd like?
Yeah, maybe you could give us. Get a bit of feedback on this one. Maybe you could just share with us a little bit of the history, say from the 1900s when Einstein did his thing, and then go from there.
Yeah. Okay. Well, it's fair. It's funny because one thing that Craig often says is, you know, traditionally atheists have thought the universe was eternal, and he seems to be doing this. It looks like to me that he's trying to set up, you know, the atheists got it wrong and the theists got it right. But the truth is, I think almost all scientists, whether they were, you know, the scientists who were interested in these sorts of issues, it was a common belief, shall we say, that the universe was eternal. And it's not just atheists that said that. Isaac Newton, who was a Christian, said that, because of course there wasn't any evidence until the 20th century that the universe was anything but static. What happened is in 1915, Einstein published his general theory of relativity. And these give you a set of equations that, it's a theory of gravity, and it allows you to model the evolution of the universe. And in the 1920s, Friedman and Lemaitre showed that Einstein's theory really implies a dynamic universe that's either expanding or contracting. And Lemaitre in particular pushed the idea that the universe expanded from something he called a primeval atom. So there was a sort of, he was very much inspired by radioactive decay, which was a new discovery back in those days. And he imagined this sort of atom sort of sitting there, and then it started to decay and caused it to expand. And so that was being pushed in the 1920s. And quite shortly after that, Hubble discovered that if you look at distant galaxies, they're moving away from us, and you can plot that relationship, and the further away they are, the faster they are moving away, which is exactly what you'd expect if the universe is expanding. However, the idea that it expanded from what we call a singularity, and what a singularity is, if the universe is expanding, we could wind the clock backwards and say, well, if we look backwards in time, it's contracting. And according to relativity, it gets to a point where certain features of the universe all become infinite. So the pressure, the density, the temperature, the space-time curvature, they all become infinity. So you can't continue your backwards evolution indefinitely. You get to a point where you sort of have to stop. And it was argued that was the beginning of time. But in the 1920s, the singularity theorems assumed that the universe was perfectly symmetrical. And that's a very unrealistic assumption. I mean, we obviously know that's not true. So people didn't take it quite so seriously. And another problem that developed was you can use the Hubble expansion to work out, when the expansion started, when the universe was born, if you like. And in those days, it was determined that the universe was 1.5 billion years old. Well, even in those days, people knew that that was ludicrous, that the Earth was much, much older than that. And there were stars that were known to be much older than that. So that was a very serious problem. And so people came up with an alternative explanation for the expansion. And this was proposed by two cosmologists called Bondi and Gould. And it was championed by Fred Hoyle, which is something called the steady state. So that, yes, the universe is expanding, but new galaxies are born in between the expanding space. And so the universe is sort of, in some sense, in what we call a steady state. It doesn't have a beginning or an end. And it's sort of the same over all spaces and all time. In the 1960s, and there, people say that model was proposed because, it was atheist Hoyle who didn't like the idea of a beginning. But there's a few things to say about that. One, there were a number of theologians that backed the steady state and said it proved God. And why would the steady state prove God? Because there's this continual creation in the steady state, and there are phrases in certain religious texts where God is described as the sustainer of the universe. So they interpreted the steady state as being the God sustaining the universe. There were obviously good scientific reasons to challenge the Big Bang, because at that point the Big Bang looked kind of silly because it was predicting this age of the universe that didn't make sense. Then in the also I should say that Lemaitre, who came up with the Big Bang, he was a Catholic priest as well as a very fine cosmologist, and the Pope wanted to use this as proof of God, and Lemaitre actually wrote to the Pope and said, don't do that, this is a bad idea, we should keep our science and theology separate because scientific theories are often revised, and I think it probably was sage advice. Nevertheless, of course, many apologists have ignored Lemaitre's advice and try and use it to prove God. So what happened was, in the 1960s, more and more evidence built up that the steady state model proposed by Bondi and Gold was wrong, and the Big Bang was right. Then what happened was, in the 1960s and 70s, Roger Penrose and Stephen Hawking came up with new singularity theorems. And what was special about these theorems is they didn't need this crazy assumption that the universe was perfectly symmetrical. They were able to show that you can relax that assumption and still have a singularity. So that put the singularity on a much firmer footing. And so the situation, I think, in 1979, when Bill Craig published his Kalam Cosmological Argument, was the theory seemed to be confident that there was this beginning, there was this singularity, and then the observations were certainly backing the Big Bang. There were many different observational pieces of evidence that all came together. So one certainly can say in 79 it was the case, there was a consensus, the universe had a beginning, that beginning was justified by the singularity theorems and the observations for the Big Bang. But things changed ironically, in 1979. What happened was there were a number of problems that were known to be present for the standard Big Bang model. And a cosmologist called Alan Guth at MIT, who's now at MIT, he found a way to fix all of these many problems at once with something he called inflation. And inflation is a very brief but very rapid expansion of the universe. Just to give you an idea how rapid it is, the observable universe would double in size in something like 10 to the minus 37 seconds. So for those that don't know what that means, it's something like, what is that, 10 trillionth of a trillionth of a trillionth of a second. So it's fast. The bottom line is fast. So this crazy fast expansion solves all of the many problems that the Big Bang theory was facing. So people were very impressed with this inflationary theory. And since then, there's been a lot of empirical evidence to support the inflationary theory. Although I wouldn't say it's for sure yet, but it certainly is the leading horse in the race for understanding the early universe. Now, the thing about this inflation theory is that it violates one of the assumptions of these singularity theorems, the Penrose-Hawking singularity theorem. So they didn't need to have this crazy assumption of a perfectly symmetrical universe, but they still have assumptions. One of the assumptions seemed like a very safe assumption. Gravity is always attractive. I throw something up, it comes down. I mean, that's what we expect from gravity. So it seemed like a very safe assumption. But in inflation, actually gives you a repulsive gravitational force or something equivalent to it. And so it actually violates the Penrose-Hawking theorems. So now it's not so clear there was a singularity, and it's not so clear that there was a beginning. Furthermore, in the early 1980s, it was shown by a number of different scientists that inflation is eternal, at least into the future. So what that means is you can think of inflation as a very fast inflating region of space, a sort of empty space, and it decays. And when it decays, it heats up that patch of space. And that is, you could think of that as the Big Bang. What was shown was that inflation would not just make one patch of a hot material, it would make many patches. And in fact, it would make an infinite number of them. Or it would go on forever in the future, I should say. And so one could ask the question, well, if it goes on forever in the future, maybe it went on forever into the past. And so that was an open question. However, in the early 21st century, Bourdet, Guth, and Vilenkin showed a theorem that says that inflation could not have gone in forever into the past, that there's still a singularity sort of hidden at the origin of inflation. Now, I should say that there are a number of cosmologists that think even within the space of inflation, that proof is not necessarily a proof that inflation has to have a beginning. So there are cosmologists such as Anthony Geary, who's at Santa Cruz, I think. Yasunori Nomura, who's the director of the Berkeley Center for Theoretical Physics. Leonard Susskind is one of the founders of string theory. All of those have said, actually, no, we don't agree with the proof by Vilenkin that inflation has a beginning. However, even if they're wrong and inflation does have a beginning, there's another assumption hidden in the Penrose-Hawking theorems. I mean, there's a few assumptions, actually. But one of the most important ones is that gravity is always described by Einstein's theory of general relativity. And that's, Einstein's theory is very well tested. I mean, the recent discovery of gravitational waves is a very accurate test of Einstein's theory. When you get in your car and you use your GPS or walk down the street and use your GPS, that's a test of Einstein's theory, because those satellites, they actually have general relativity programmed into them. So they have to make accurate measurements of the time it takes for a signal to go from your phone to a satellite. And they actually have corrections for general relativity in them. However, general relativity is what we call a classical theory of physics. So what that means is that you can sort of cut things up forever, basically. There's no smallest unit. Another way, in mathematical terms, if people that know maths, classical theories are described by what we call real numbers, so that's numbers that we are familiar with, 1, 2, 3, 4, 5. Quantum mechanics is a different theory. This is a theory that describes very small things. Or not just very small things, but it's what you need to describe very small things. And so subatomic particles, and it's a fundamentally different theory. It has what we call discreteness, which says there's minimum sizes to things. And also, rather than just using real numbers, it uses a different type of number called complex number. I won't go into the details of that, but the bottom line is different mathematics and different physical assumptions. For the most part, when you're talking about the evolution of the universe, you can just ignore quantum effects. These effects are important when you're talking about subatomic particles. They're not necessarily very important when you're talking about big things. However, if the Big Bang Theory is true, then the entire observable universe will have a point in its early stage where it's smaller than an atom. And then quantum effects will become very important. So it's not a good idea to use a classical theory. So we think that general relativity breaks down and needs to be replaced by a theory that combines quantum effects with general relativity. So people call this a quantum theory of gravity. And what's happened since the 21st century is that, well, we don't have a well-tested theory of quantum gravity, but people have developed theories of quantum gravity. You might call these our best attempts so far. And string theory, of course, is the most famous, but there are others, such as loop quantum gravity, and another one is called Harjava-Lifshitz gravity. What's noticeable is that the discreteness introduced in these theories seems to prevent singularities from forming. And what is a common prediction from these theories is that the space-time acts a bit like a sponge. So if you imagine a sponge, if you pour water on it, it absorbs water. It's water absorbing. However, the sponge cannot take an indefinite amount of water. Eventually, you pour water onto the sponge, and the sponge is full up. And now it switches from becoming water absorbent to water repellent. Similarly, this is a very similar effect to what these quantum gravity theories predict happens at the Big Bang. Eventually, space-time cannot keep taking more stuff into it. And so eventually, the stuff will just bounce back out. So the Big Bang becomes a big bounce. And what's typical is you see a sort of hourglass structure to the universe. So if our universe is, let's say, it's expanding, if you wind the clock back, it's contracting. But it gets to a point where it gets to its maximum density. The density in these theories cannot become infinite. So it has a maximum point of density, and then it bounces back out. So our universe looks like a sort of hourglass expanding out to infinity, and then expanding out to infinity, going the other way, or contracting from, depending on which way you're looking. So it seems then that our best attempts at quantum gravity are telling you the Big Bang is not the beginning, but we don't know that these attempts are right yet. They haven't been empirically checked. There are proposals for how we might check them, but it hasn't happened yet. So we don't know whether the universe really did begin at the Big Bang. And there's a lot of reason, therefore, because of these quantum gravity theories, to suggest that perhaps it didn't. But of course, the very important thing to stress is that in science, we have to have empirical tests to check, no matter how reasonable your theory seems, it must be checked by experiment. And at the moment, there's no experiment that can tell us what really happened at the Big Bang. And so we don't really know whether it was the beginning. And the statements made by many theologians, and not just theologians, but popularizers of science, where people say, oh yes, the Big Bang has proven the universe had a beginning, I would say those statements are not justified.
Perfect. So one quick question that, because you mentioned obviously Penrose and Hawking, and one of the questions in the chat, which I'm sure you'll easily be able to answer, is about, where is it? Here we go. So Penrose said the universe in which life can form his calculations were like 1 to the power of 123. Yeah, I think that's not cosmology though, is it?
123, I think. Oh, it's a very large number, certainly bigger than what your questioner just said. I think it's 1 to the 10 to 123 or something. It's an enormous number.
Yes.
Yeah. So you want me to talk about that?
Yeah, just briefly answer that question if you would.
Well, first off, so people have claimed that this is incredible fine-tuning for life. And that is to misquote Penrose. That's not what Penrose is saying at all. What Penrose is saying is that the early universe's entropy, if you were to choose it at random, would not come out at where it was, at that low. I mean, it could have been much higher. It's not fine-tuned for life. It's nothing to do with life, because the entropy could be enormously higher, and life wouldn't care less. So most of that entropy is where? It's in black holes. So if those black holes evaporated, so what? It doesn't affect us. So it's nothing to do with life. It's not fine-tuning for life. But what the statement that Penrose is trying to make is that it wasn't just randomly chosen. There's some mechanism that puts the entropy into a low state. And he is arguing for a cyclic cosmology. And that's often missed out when people quote Penrose in this context. What he's saying effectively is that the Big Bang was not the beginning, but there was something before the Big Bang, and that thing before the Big Bang put the entropy into a low state. That there's a deterministic law that basically says the entropy must be low as you go through the Big Bang. So he's not saying it's fine-tuned for life. In fact, he says for sure it's not fine-tuned for life. Sean Carroll has made this point, and I'm confident Roger Penrose agrees with that point. And so it's not fine-tuned for life. What Penrose is basically arguing was it wasn't just set randomly or haphazardly. It was, in fact, put there by some process, and the process, Penrose argues, is a cyclic cosmology.
Perfect. So can you just, because you mentioned it a few times, can you just explain what entropy is for people?
Sure. So the rough understanding of entropy is a level of disorder, but a more precise definition, I mean, there are different ways to define it. It's the number of micro states that gives you a given macro state. So let me try and explain what that means, because people might get confused by those terms. So there's lots of analogies you can give. So imagine you have a big bucket full of Lego bricks, and they're all different colors. And you're going to build, let's say, a wall made out of these yellow bricks. Sorry, Lego bricks. So let's say most of them are yellow, okay. But there are some pink bricks and some blue bricks. Maybe you make this brick wall, and you put some blue bricks here and blue bricks here. Maybe you put some pink bricks in a sort of shape like this, and it will look like a face. Imagine it's quite easy to imagine, I hope, that you could make a face with different colored yellow Lego bricks. Now, imagine you took the wall down and you reassembled the bricks at random. Then you'd have a bit of a mess. It wouldn't look like anything, probably. Now, the different ways you could rearrange the bricks to give you a mess is quite high. But the different ways that you could rearrange the bricks to give you like a face or some other shape is low. So we would say that the face is low entropy and the mess is high entropy. So the idea is it's how many different ways can you rearrange something to get the same thing? So that's really a better definition, I think, of entropy. So what Penrose is arguing is, because entropy goes up in time, if you go backwards in time, it must be getting lower. So, and if you look at the Big Bang and you look at the physics of it, it looks like the Big Bang is enormously low entropy, and that's a mystery. Why should it have such low entropy? But it's not, and you could argue that it's fine-tuned, but it's not fine-tuned for life. So a God that wants life is not going to explain this low entropy. Because you could explain some fine-tunes via a God, let's say, or by a multiverse. And you could say, yeah, the multiverse has a selection effect. Living things can only see certain conditions that are suitable for life. Or you might believe in God, and you might say, God wants life, so he makes the entropy, consistent for life. But neither of those are going to explain why the entropy was so low, because the entropy could have been enormously higher and life would have been fine. So life is not going to be a likely explanation for the low entropy. And that's why he's arguing for a cyclical cosmology, which he claims does explain the low entropy.
Perfect. Okay. So I think, the questioner might be misunderstanding this, but the question in the chat is, the number can't even be imagined. It's 1 followed by 123 zeros. That's his calculation on the occurrence of the universe coming by chance. And from what you're saying, that's a misunderstanding.
Well, it isn't. It isn't. I mean, depends what you mean. Yeah, Roger Penrose is arguing that the low entropy state did not get there by chance. It came there by a process that is described by the laws of physics. And in his case, he's arguing for a cyclic cosmology. So it's not by chance. You're right. I mean, he's saying, no, it's not by chance. There are other people with different proposals. And also, it wouldn't be by chance. So there's no statement that it's chance or God. There's plenty of non-chance things that happen in physics. If I pick this memory stick up, it's not random which direction it's going to go in when I let go of it. It's going down, right? That's not chance. That's following the laws of physics. And this is what Penrose is arguing. He's arguing that there are laws of physics that will put the universe into a low entropy state. And he's arguing in that sense, yes, it's not chance, but not chance does not mean design.
Yes, because of course he's got his model. So while we're on that, maybe you can briefly explain Penrose's model for an eternal universe. Yeah,
sure. So this is quite a novel suggestion. As I said, most cosmologists today think that in order to understand the Big Bang, you need a quantum theory of gravity. And that will sort of remove the singularity and so on. Penrose's model doesn't really use that approach so much. It certainly doesn't use quantum effects of the Big Bang. There are quantum effects happen later on. But basically, he argues, it's a very clever idea. Whether it's right or not remains to be seen, but it's an incredibly inventive idea. What he argues is that there's another assumption built into his Penrose-Hawking singularity theorem that we haven't addressed. And that is that space-time is described by what's called, I'll give you the technical name and then I'm going to explain what the hell I'm talking about. It's called a Lorentzian manifold. So what does that mean in plain English? Well, it means that you have 3 spatial dimensions and 1 time dimension, and that there is mass in the universe. So things, like this bottle of water or whatever, me, this, they have mass. Now, it turns out in relativity that space and time are connected to each other. So in order to have time, it turns out you need mass. And in order to have a notion of scale, you also need mass. What Penrose argues is that in the very early universe, there wasn't any mass. And so you have to use a different type of geometry and to what he used for his Penrose-Hawking theorems. And this is called a conformal geometry. Now, what does that mean? Well, it means, so the analogy I'd like to give is a chessboard. Oh no, maybe a simpler one would be a triangle. Imagine a triangle. What do the angles of a triangle sum up to on a flat plane? They sum up to 180 degrees. Now, if you double the size of the triangle, the angles don't change. It's still 180 degrees. So the angles are what we call conformally invariant. So i.e. they don't care about a change of scale. So what Penrose argues is that the space-time has to be conformally invariant in the early universe. And then in the very late universe, eventually mass will disappear from the universe. That's a controversial assertion, but maybe it's true. And if that's true, it's conformally invariant again. So the universe sort of forgets how big it is, and it becomes a state with just energy and no sense of scale, and no sense of a scale of time either. So the indefinite expanding universe is then sort of transforms into a new Big Bang. And this goes from cycle to cycle forever, into the past and into the future. It's a very strange cyclic cosmology, because we usually think of cyclic cosmologies that are expanding and then contracting, sort of going like this. But his doesn't do that. It's always expanding. So that's a very novel idea. And one of the you know, whether it's right or not, who knows? But the thing that I think is the most attractive about it is that it does explain why the entropy is so low at the Big Bang. This is why Penrose is saying, yeah, it's not random. There is an explanation. It's this conformal rescaling. And what happens is, in his model, the entropy is sort of in black holes. I mean, that's not controversial. He claims that the black holes lose information, which is controversial, but there's arguments both sides and no one knows what's right. So it's certainly a plausible solution. It's certainly implied by general relativity. If you just take general relativity, it seems obvious that information is destroyed in black holes. And because of that, you lose what's called the gravitational degrees of freedom. So let me try and explain what that means. Degrees of freedom is a phrase you'll hear scientists use a lot. What it is how many numbers it takes to describe something. So you lose the gravitational degrees of freedom when the black holes evaporate, and that effectively resets the entropy, because all that entropy is effectively thrown away as you go into the next eon. So it's not that the second law is violated. The second law is never violated. You know, in some sense, you know, it's always going forward, but you have to redo your counting, and now you're left with a low entropy condition. So that's his model.
Great. So that's obviously one that it's a possibility for an internal universe in the past.
Yes.
Okay, good.
Yeah.
Cool.
I should add that I'd like to just add that Bill Craig was asked about this model on his podcast, and he said, "Oh no, this." Now, what I think would have been a legitimate thing for Bill Craig to say is, "Well, I don't think this model has much chance of success. I don't think it's very realistic." That would have been a reasonable criticism. But interestingly, that's not what he said. What he said was, "This is a model that is not even a cyclic model. The eons aren't one after another. Instead, this is a sort of a multiverse model where you have two universes that appear out of nothing and then sort of branch in a sort of multiverse." And that's just wrong. I mean, that's ridiculous as far as I'm concerned. And don't take our word for it. We made a film with Roger Penrose, and Penrose explicitly said that was wrong. And you only have to think about it. The way the model works is that the gravitational degrees of freedom are killed off in the prior eon. So there has to be the eon, and there is gravitational radiation going through from one eon to the next, which is impossible in a multiverse. They don't communicate with each other. Whereas in cyclic cosmologies, they can communicate with each other. So, I mean, it's a completely wrong way to describe it. And I think he misrepresented the model, whether it's deliberate or whether he just doesn't understand it, I don't know. but I think it is a misrepresentation of the model.
Yes, and of course, that's what Roger said, isn't it?
Yeah.
So I thought just at this moment, I thought a moment of potential lightheartedness. A commenter said, did Phil find any amazing knowledge of cosmology in the verses of the Quran? I just thought I'd break that for a moment.
I have read the Quran, and I didn't find any amazing cosmology in the Quran.
Great, so we've answered that one. Perfect. So have you answered, do you feel like you've fully given us a reason as to why the second premise of the Kalam, the universe began to exist, is we shouldn't take that as being a solid suggestion at this stage?
For modern cosmology, I think the most cosmologists will say we don't know whether the universe had a beginning. Whereas I think if you ask them in the 1970s, they would have said we do know the universe had a beginning. But I think that view has been revised. Now, one thing I'd like to say about that before we if we want to move off that, is Bill Craig will often say, well, we don't, when cosmologists say they don't know the universe had a beginning, they mean they're not certain. And I don't think that's what they mean. It's not a question of a lack of certainty. It's a question of we don't have any empirical evidence of what happened at the Big Bang. We only have empirical evidence of what happened after the Big Bang. So it's not just, oh, you know, in science we don't talk about certainty. It's much more profound than that. Of course, there are other reasons that people have suggested the universe has a beginning. So there's arguments from the second law of thermodynamics, and there's other philosophical arguments that we can go over if you wish. Do you want to do those, or?
Okay, so before we do that, I just want to finish off with the Kalam. So that's basically, you've sort of given a reasonably good explanation of why there are other theories out there, why, and they sort of, there's answers to basically many of the questions that theists ask. When I say answers, there's possible answers to many of the questions theists give, which is, oh, did the universe create itself? Was it static, or did it have a beginning? And apart from creating itself, I think you've dealt with the other two, and I think we interviewed somebody recently, didn't we, who suggests there's a model where the universe can create itself.
There is that suggestion. I mean, you might think it could be crazy. How can the universe create itself? And I would agree that's impossible as long as time is always running forwards. However, there are solutions to general relativity called closed time-like curves. And this has been shown that these solutions do exist in the theory. And if there's a closed time-like curve, what that means, so in general relativity, space and time can curve. This is what explains gravity. And so the question is, can time curve back over onto itself and make a loop? And there are solutions to general relativity where this can happen. And it has been suggested that when you get back into the very early universe, things do get more curved, and space-time does get more and more curved. And it's been suggested that maybe that time can curve back on itself and create a loop. And so with a time loop, now it's, you know, conceivable the universe could create itself. That is possible if closed time-like curves exist in nature. Of course, we don't know whether they exist in nature. They exist in the theory, but that doesn't tell us they exist in nature. So this is a conjecture, but it's certainly something that's been suggested by, you know, some very respected physicists. And it is known to be a solution in general relativity. But what's not known is, can it really exist in reality? And there's a big debate in the literature about that. And, you know, Stephen Hawking has suggested what he calls a chronology protection conjecture. But of course, that's a conjecture, you know, it's not a fact. And some people think, well, no, you know, there'll be some law that says closed time-like curves cannot exist. But at the moment, again, it's uncertain, and we don't know. I don't think anyone's proven they can't exist, but so the fact that they seem to be allowed by the theory, maybe, doesn't tell us whether they exist in reality.
Yeah. Okay, cool. A question here from one of our viewers. Simon asks, is it possible that the universe can be created in more than one way? I'm not sure. That seems a bit of an ambiguous question.
Yeah, no, okay, I think I get the question. Yeah, I think possible that it was created in more than one way. So there might be more. Yeah, I mean, if you think about it, you know, if you imagine one model of the Big Bang is correct, you know, maybe there are other models that are correct in other circumstances. I mean, you don't really see this much in the literature. It's usually just sort of one thing that people are explaining. But there are some exceptions. I'll give you an example. So, you know, inflation is thought to sort of create our Big Bang by the decay of this inflating space. And then people have suggested, well, maybe we could actually get the inflating space to do it again. Maybe we could even make space do that. And there's been a suggestion that maybe we could actually make a universe in a laboratory. This is quite interesting because what would it look like to the creator of that universe? Well, it would only appear to them as a little black hole, which would then evaporate as it becomes disconnected. It would create its own space. It wouldn't invade your space. But you could have a natural history, and you might make a new universe, and that might have effectively an artificial history. So I think, in principle, it's possible that there is more than one way, if you like. It's you know, I don't think there's a logical reason why there couldn't be more than one way to make a universe. But I think, you know, cosmologists it's difficult enough to show one way, and that's what they focus on.
Perfect. What would be your response here? Because obviously somebody's brought it up, and I hear this a lot as well. What you're saying basically is based on the opinions of others, and it's just opinions. That's some probably you've been, you know, that's been said to you, it's been said to me before as well. So in other words, we don't have knowledge or absolute truth in inverted commas. Well,
first off, science doesn't deal in absolute truth. So anything in science is not about absolute truth. It's about, you know, I think that's an unreasonable standard. It's just not needed. You have, you know, the best evidence that you have, and you make conclusions from the evidence that you have. And sometimes the evidence is overwhelming, and therefore it's kind of silly to deny. In the case of the early universe, we do have overwhelming evidence for our descriptions of the universe up to a certain time in the past. So certainly up to like 1 microsecond after the Big Bang, we're very confident, and the evidence, I think, is very clear as to what happened. As you get to very earlier and earlier periods, it's true, we don't know what's happening, and that's kind of my point. You know, we don't know what's going on. Therefore, any confident statement about what happened at the Big Bang is inappropriate. I mean, you can certainly make arguments that this is likely as what happened. But you shouldn't make any statements with any high degree of confidence. You know, the statements that we can make about other things in science, you know, like the Earth orbits, you know, around the sun, and, you know, Jupiter is the biggest planet in the solar system. You know, there's lots of galaxies. These sorts of statements, you know, they're not really up for dispute. They're overwhelmingly supported by enormous amounts of evidence. Statements about what happened at the Planck era, you know, the very moment of the Big Bang, any statement about that we're not confident about. And that's kind of my whole point, because people that argue cosmology shows a beginning, that requires a high level of confidence about what happened at the Big Bang, and that is confidence that would be inappropriate. We don't have that confidence.
Yes, and of course theists want to jump on that by going, well, you don't have confidence, that allows us to assert something, and they seemingly do it with confidence. And from what I can see, certainly with the people that I deal with, they can only use a philosophical argument because they haven't got anything in science, they don't understand science, and so all they can attempt to use.
Okay. But you see very, very commonly many apologists using science of cosmology to say, yes, we know the universe had a beginning. And that is what I think is unjustified. Science doesn't show that. We don't know whether the universe had a beginning or not. It might have. I'm not claiming it didn't. As I'm not saying that the second premise of the Kalam is false. But we don't know it to be true. And if you don't know if your premises are true or not, you can't get to your conclusion.
Correct. And I think that's the thing that's sometimes a little annoying, is that the smartest people on earth don't know the answer, but then we have, let's say, lay people like myself or theists or whoever it is. Well, hopefully I wouldn't do it, but lay people in general coming along and saying, well, no, the universe had a beginning, and misinterpreting science. And I think that's the, the irritation I have.
Yeah, but I should say there are many popularizers of science that do the same thing. So it's not necessarily always their fault, but some people, on the apologetic scene do seem to do their homework, but they don't seem to actually live properly. And I think if you do your homework, you'll see, I remember Bill Craig said something like, you can find this in any textbook. Well, you just have to look at a textbook, and I've got my textbook in cosmology, and it says opposite of what he says. It says, we don't know whether the universe had a beginning because we don't understand quantum gravity.
So a quick one, I'll just go back to, one of the viewers here seems to challenge you didn't give a definition specifically, but here's what he's put. The term entropy describes the degree of thermodynamic disorder in a closed system like the universe. At maximum entropy would describe the heat death of the universe, which is kind of what you said, but in a slight...
Well, as I say, there are different ways to describe it. But go on. So what's the question?
So he's basically saying your definition of entropy is incorrect.
It's not incorrect. Well, I don't think it is. But they're equivalent. I mean, they're not contradictory statements. The rearrangement from the micro to the macro states implies, that the amount of usable energy is going down over time. So I don't see what the problem is. Yeah.
Here's obviously what I hear a lot is words every cosmologist use: can be, could be, maybe, probably, might be, no surety. And I think this is the thing I hear over and over, which is a little bit frustrating to me. And obviously you've mentioned something about that. So they because there's not, quote, certainty, that's license not to take any of these things seriously or to look into them or to just dismiss them in some sense.
Well, of course. So first off, I mean, one thing where I would agree with Bill Craig is science is not about certainty. Science is about following the best evidence. And there are many, many statements in cosmology. I mean, there's a sort of spectrum of confidence levels, shall we say, from, we've got absolutely, right at the bottom, we've got no reason to take that seriously. That's just pure assertion, to something that's been overwhelmingly confirmed by experiment. And there's a whole range in between where, so take inflationary cosmology has been confirmed, I think, by a number of experimental probes, but it's not quite for sure that it happened yet. But the evidence has been building up and building up, and I think it's sort of, looking like a strong, the front runner in the race, as it were. But it's not quite across the finishing line. Another example is dark matter, where there's very strong evidence, I think, that dark matter exists, but we're not quite there where we can rule out, competing ideas to dark matter, maybe some modification of gravity. Those ideas don't look as strong to me, and I think to most cosmologists, but it's not for sure yet that they're wrong. Similarly with inflation, there are competing ideas to inflation. Penrose's CCC is one, there are others. They're generally cyclical cosmologists that are competing with inflation, and they're not necessarily been ruled out, so it's not for sure yet. And so there's this range of confidences. So it depends on the statement. Some things we are extremely confident about, and others we're not. And one of the things that we're not confident about is whether the universe had a beginning.
Yes, and I think there's a confusion sometimes between some of the things we know and those things being put together and then giving you a theory which we don't have. We don't know it is true, because like you said, there's certain things that we do know, and then when you put them all together, the level of certainty goes down. And so I think, because I'm looking at some of the comments here, that's kind of the misunderstanding that I noticed at least one commenter making. Oh, well, cosmologists claim they know things, but then when they open their mouths, they don't have surety.
Well, it depends what you mean by the word know. I think when you say I know something, I think that means you've got overwhelming evidence for it. That's my definition of no, the one that I would use. And there are lots of things where we do have overwhelming evidence. So, the standard picture of the universe where, you know, it's sort of expanding over time, and it's getting, basically what we mean by that is it's getting colder and less dense. That I think we do know. So it was hotter and denser in the past. I think we know that. We can go back at least, you know, we can go back roughly 13.8 billion years, and we're pretty confident about many things, and not everything. I mean, there's still lots of mysteries out there, no question about it. And certainly what actually happened at the very moment of the Big Bang, that is still mysterious, and we don't know what happened there. But that's kind of the point that I'm making. Lots of people claim that we do know what happened there, that it's the beginning of the universe, but that's not a valid claim.
Yeah. So, so you feel like you've adequately explained the second premise. Is there anything you want to say on the first premise, or is there anything you want to add on about?
Well, with the second premise, we only talked about the cosmology, the modern Big Bang cosmology, and why it doesn't support a beginning. We didn't talk about the second law argument, and we didn't talk about the philosophical argument.
Yes.
We can skip those if you want, or go on to the first premise, up to you.
I would like you to talk about the second law, to explain what it is for people who don't know, and what your objection is to people using that to claim the universe had a beginning.
Okay. So where people use the second law as a proof of the beginning of the universe is that the entropy is going up over time, and it will get to some point of maximum entropy, and therefore it couldn't have been an eternal past, because then we would already be at the maximum entropy.
Okay, before you carry on, can you just explain what the second law of thermodynamics is, and then go from there?
Well, I think we did describe that with the microstates and the macrostates.
Oh, okay, cool.
Yeah, and then your commenter said it's a measure of disorder, but those two things are the same. Basically, the more microstates that give you a certain macrostate is a measure of disorder. So it's getting more disordered over time. What's relevant here is there's less usable energy in the universe. So basically what will happen in the far future of the universe is all the structure will go away. So all the galaxies and the stars and planets, they'll just sort of turn into a soup of radiation. I mean, one way to think of it is this. Imagine you put your pizza in the oven, yeah? You take the pizza out of the oven, eventually it comes into thermal equilibrium with the room. So it cools down. And that's what the universe is doing over time. It's cooling down. And it's going to get into a state of thermal equilibrium. But we're not at the state of thermal equilibrium now. So the argument runs this way. If the universe was eternal, we would already be in a state of equilibrium. So the universe can't be eternal in the past, because we're not in a state of equilibrium. So that's how the argument goes. Now the question is, why is the argument wrong? Well, because when you look at the Big Bang, you see it's in a very, very low entropy state. So the question is, why is it in a very low entropy state? And lots of physicists have looked at this and have proposed dynamical ways in which the Big Bang can sometimes put the universe into a low entropy state. And we talked about Roger Penrose's CCC model, and that does exactly that. And that's a cyclic model. It's an eternal model. And there are other proposals. I interviewed Alan Guth, so I hope people watch our film with Alan Guth. If you want to see it, Google before the Big Bang eternal inflation, and you should find it. And he also thinks the universe is eternal into the past, and there are processes that puts the universe into a low entropy state. So therefore, there's no reason to assume that the universe can't be eternal because of the second law. You're assuming that the Big Bang has nothing to say about why the universe is in a low entropy state. And in fact, many cosmologists think the Big Bang may, or processes connected with what happened before the Big Bang, may put the universe into a low entropy state. And if it does that, then there's no conflict with the second law and an eternal universe.
Great. Okay, I'll put your link to that video into the chat as well for people who are interested. Go and watch Phil's video. I've watched that one. That's number 4 in the series so far, and the one that I actually enjoyed the most. Perfect. So do you want to then just address the philosophical argument?
So the philosophical argument is that you can't have an infinite past because then we sort of wouldn't get to now. And there's a number of problems with that argument. First off, I think the argument just assumes that there is a beginning that's infinitely far into the past. But that's not the case. If the universe didn't have a beginning, there's no beginning. The universe doesn't have to get to now. The universe isn't an object traveling through the universe. You know, it doesn't have to get to anywhere. Similarly, and Bill Craig has admitted this, this argument depends on a certain notion of time that doesn't seem consistent with relativity. Because in relativity, there isn't a unique now that the universe has to get to. Different observers have different notions of now. So this argument sort of, it definitely appeals to your sort of intuitive notions of time. But what relativity shows you is that your intuitive notions of time are wrong. So time doesn't work that way. So I think, now of course, Craig has argued for an A theory of time, and that might help that argument, but we certainly don't know the A theory of time to be true. And even philosophers, that the survey that I know was in the Phil Paper's survey, and they surveyed philosophers, and twice as many philosophers back the B theory than the A theory. And I think most physicists would back what's called the B theory. These are different notions of time, but that argument requires this particular notion of time that is sort of consistent with your everyday notions of time, whereas relativity implies a different notion of time and therefore undermines that argument. But even, if you forget this debate about notions of time, that's another point. We interviewed Roger Penrose, who's one of the world's leading mathematical physicists, and he's obviously saying the universe is eternal into the past. And we said, how can that be? Well, one thing that he pointed out was in relativity, massless particles don't have the normal notion of time that we're used to. So 1 second, a billion years, Google years, it's all the same to them. So they can easily transverse the infinite, as it were, because they don't have this notion of time like we have it. So that's another thing to say about that. So I think this argument may have made sense in the days before relativity came along. But now it doesn't. And in particular, I should say, people say, oh, you can't have an infinite. No actual infinite can exist. But again, when relativity came along, it showed you how you have a beginning of the universe. How do you have a beginning of the universe? Via a singularity. And what do we know about singularities is that the temperature, the pressure, the curvature, the density are all infinite. But if you can't have an infinite, then it seems to be maybe you can't have a singularity. And then you've got to say, well, how do you get a beginning of time then? Because that's the mechanism to give you the beginning of time. So then you'd have to maybe have some other mechanism to give you a beginning of time. But that's, not so clear how you would do that. I mean, there are some proposals to how you could do it, and they might be right. But it's certainly not, they're quite controversial. And certainly the people that have argued the Big Bang proves the beginning are arguing for a Big Bang singularity. But that has infinities in it. So I think there's a contradiction there between the people that use the Big Bang argument and the philosophical argument. To me, there's a conflict there, because the Big Bang, to get a beginning from the Big Bang, you generally assume a singularity, which has infinities. But you already told me with your philosophical argument, you can't have infinities. So which is it? So
what would you say as a response then? Because some people who are not, as well versed as you would go, no, we're not thinking of those sort of singularities. We're thinking about actual objects. So actual infinities being like the silly things I hear is like bananas, or the more philosophical would be Hilbert's hotel.
Well, I don't know what you mean about bananas.
Somebody basically just, we can't have an infinite number of bananas, which is obviously amusing.
Well, we won't be able to count an infinite number of bananas, that's true. But that doesn't mean you can't, there is no infinite number of bananas in the cosmos. I mean, I don't know how many bananas are in the cosmos. Maybe it is an infinite number, I don't know. And I don't think they know. It's certainly true that we can't count an infinite number of them, but that just tells us about how we count. Now, Hilbert's hotel is very interesting. But that just tells you that infinities are counterintuitive, that there are some strange results when you include infinities. But Hilbert himself accepted infinity as a mathematical concept. He didn't think that it was physically realized in the universe, but that's not a question for mathematics. That's a question for physics. And physics can't tell us whether the universe is infinite or not. It might be, it might not be. We don't know. And there's certainly nothing in physics that rules out the universe being spatially infinite or infinite in time. And again, if infinities are not real, that would surely that tells you singularities aren't real. And if singularities aren't real, then I'd like to know what your justification is for saying cosmology gives us a beginning. How do you actually? So in relativity, you know, the universe is expanding, and there's space, there's time moving forward. How does time just stop? Now, with a singularity, you actually have a mechanism for how time can stop. But that has infinities in it. So if you don't like infinities, let me know how you get time to stop. Now, there are proposals for how this could happen. But again, they're controversial, and we don't know if they're correct or not. So again, we don't know if there's a beginning or not. There might be one. Again, I want to stress there might be one. I'm not saying there isn't one. And there are models that have a beginning, but we don't know if they're correct or not.
Yeah, and I guess the takeaway point for us as non-believers is when people assert, for example, that actual infinites cannot exist or it's impossible for them to exist. That's the mistake that they're making. Not that it's not possible, but just for them to say it's impossible is the main point.
That's just an assertion. I mean, what I would encourage people to do is go and say something like physics forums and just say, you know, ask people. I mean, it's probably on their FAQ, I think. You know, or there's lots of physics FAQ. Is the universe spatially infinite or not? Okay. And cosmologists do not rule out that it is spatially infinite. In fact, there's a geometry that's consistent with the universe being spatially infinite, and it's called a flat geometry. So what does that mean? It means that if you have two light rays going through space, that they, you know, won't, you know, if the universe was sufficiently curved, like the surface of the Earth, they would come back and hit you. You know, if you sent it out here, it would curve around and come back and sort of hit its source. Yeah. But in a flat geometry, they just go on in parallel forever. So people have made measurements of the universe, and the geometry comes back flat. So that's consistent with the universe being infinite. And a lot of cosmologists think the universe is spatially infinite, including some of the cosmologists that theists like to quote. I mean, Vilenkin, he does think the universe is spatially infinite. So, you know, I find it amazing. People quote him all the time because he is a cosmologist that believes the universe had a beginning. But they're also making the argument that, you know, infinities cannot exist. But so why don't they quote Vilenkin again? Because, of course, he thinks infinities do exist. You know, the universe is spatially infinite as far as I understand his writings. So now the flatness of the universe doesn't prove the universe is infinitely big, because it could be that there's the curvature beyond what you can measure. But it does show the universe has to be certainly bigger than what you see. And if there is any curvature, which would mean it's possibly finite, we can't measure it. It's beyond our horizon, as it were. So we haven't detected any noticeable curvature in the universe. So that's consistent with it either. So the options on the table are it's either infinitely big or it's just much, much bigger. And I think both options are considered viable by pretty much any cosmologist. So the idea that you rule out infinity a priori, I think is completely wrong. The only thing that I think scientists do rule out when it comes to infinity is you know, infinity that you could measure. So like if you're calculating particles hitting each other, you could look at the energy of the collision. If the energy comes out infinity, then people will say that's nonsense because you can measure the energy of the collision. Yeah. So they would say that cannot be real, but that doesn't mean all infinities are excluded a priori. They're not.
Cool. So I just wanted you to go back for a moment just to explain the A and B theory of time as if you're speaking to lay people, if you can, just so that if anybody ever brings that up, at least we've got a rough understanding of what that means.
So the terms A and B theory are really terms that are used in philosophy, and it goes back to, I think it's McTaggart. And he sort of was trying to argue, as I understand it, I'm not particularly well versed in philosophy, so I can only give you my recollection from reading it. Whereas he was trying to argue that that you shouldn't really think of time as sort of flowing as your everyday day-to-day experience. So because if you think of, well, now exists, as we traditionally think, well, now exists, the future is yet to exist, and the past no longer exists. So only now has a unique status. And he was trying to sort of argue against that. Relativity comes along and sort of really confirms that in a very, very important way. Because in relativity, people experience time at different rates. And you can show this. So if you go in a rocket, if you get on board a rocket, fly off at very high speeds, to someone left on Earth, so suppose you were to go, near the speed of light, fly off to, Andromeda Galaxy and come back, to you, not much time may have elapsed. But to the people back on Earth, it'd be an enormous amount of time has elapsed. So you would be younger, than your children, potentially, or your grandchildren, or, great, so people can't agree as to what is now, to the space traveler now might be 20 minutes has passed, but to the people on Earth now is thousands or millions of years later. And this is not something just theoretical. This is something that is confirmed overwhelmingly by experiment. This is not controversial. That there isn't really this notion of now, or a unique notion of now. So it's all sort of observer dependent. Whereas the A theory is saying there is a unique now, and that time is very much like we experience. And so these are the sort of different theories of time, A and B theory. And the B theory is often argued to sort of consist of what's often been called a block universe. But you should really think of time as like a movie, where you've just got frames in the movie, and they just exist. In some sense, sort of, it just exists eternally. The past doesn't. It's like saying there's a unique here. Like I'm here, and you're there, but to you, you're there is you're here. So we don't agree on what is here. Yeah. But what relativity is telling us is that there's not a unique now either. Now, defenders of the A theory basically then, how do they square it with relativity? Well, they have to reinterpret relativity in a particular way and reintroduce preferred frames, and they have to come up with a particular interpretation of relativity that is not accepted by most physicists, in my opinion. And interestingly, it predicts that, as I understand it, it predicts that you can go faster than light, even without sort of crazy wormholes or stuff like that. So there's no evidence for that. And I think this particular interpretation of relativity is not well supported, shall I say.
Okay, good. Is there anything else you want to say on the second premise? Because I do want to ask you something on the first premise.
I think we've covered most of the ground.
Okay.
So, one thing I should say is that a lot of cosmologists think that as I say, a rough consensus about people that work in inflationary cosmology, that it leads to a multiverse. And certainly Vilenkin thinks this, and Guth thinks this. I mean, it's quite common. It seems to be almost an inevitable consequence of inflationary cosmology. In that case, that also, I think, undermines the notion of a beginning to the universe. Now, of course, many people will be familiar with Vilenkin claiming that the multiverse has a beginning. And maybe it does. But if that's true, it's a beginning that is completely removed from any ability for us to observe it. There wouldn't be any observational consequences of such a beginning if it did occur. And of course, we don't even know whether it did occur, because theorists dispute that. But my point is, if there's a multiverse, and if the multiverse has a beginning, which it may or may not do, we will not have observational access to that beginning. And that's very important, because people like Vilenkin argue for A, a multiverse, and B, a beginning. But what you have to consider is that the beginning that they're talking about is not our Big Bang. Our Big Bang is just one of many in Vilenkin's conception. So when he says universe, he really means the whole ensemble of many pocket universes. And he's saying that this structure has a beginning, but our Big Bang is just one of many. But if there's a beginning to this structure, it's completely removed from observational consequences. So, you know, there's a lot of confusion there. You can't then use our Big Bang as evidence for that beginning, because that's really a different beginning. Does that make sense?
Yes, yeah. So a question here from one of the viewers. Phil, is there any reasonably decent theory of God out there by any good believing scientists?
Depends what you mean by theory of God. I mean,
I'm guessing scientific theory?
There are scientists, of course, that believe in God. I'm not sure they develop a theory of God. Certainly what you don't see in the literature is, you know, here's a theory of our origins that involves a God, and, you know, I can work out any sort of detailed mathematical consequences of that theory or justification in scientific terms. I mean, of course, there are scientists that believe in God, and they make arguments for why they believe in God, and you have to take those arguments on their own in each case. So does that answer the question? Yeah,
I think it was a slightly may not have been phrased that well. I guess maybe if I reinterpret it, for me, it seems to me in order for a theist to put forward a claim about the universe, they would need some kind of God claim that had some scientific, I guess, evidence, mathematics, something that we could view and attempt to falsify and do the sort of work that is being done now in the different theories.
I mean, ultimately, it has to have, in order, I think, for it to be something that we could say is true from a scientific perspective, and I think any perspective, you know, it has to have strong evidence in favor of it. So we're not, you know, there are, as we said, there's a lot of competing ideas for the nature of the Big Bang. And at no point are we going to say they are true. We're going to accept them, write them up in textbooks until they've made predictions that we can check via experiment. And people are trying to do that. You know, there's a lot of work trying to get observational consequences of some of these models and try and build pieces of equipment that can test those. And that's, until that happens, we are certainly not going to accept any of these models as being the one we accept as right. And I think, you know, personally, if you want to convince me there's a God, you need to do the same. You need to play by the same game and show me the mathematical consistency, what we should expect to see in the world, and then, you know, we have to go and check, is that true? So, I mean, it could be that our universe was created by a God. I mean, it depends on how you define God. I don't know, but in order to convince us that that's true, you know, tell us how we're going to test it.
Yeah, it seems to me that obviously there isn't a theory of God in that sense, and what some theists do, and I won't say it's all theists, but some theists will hop on or pounce on a particular theory or hypothesis has been put out by a cosmologist and then try to co-opt that in some way, but they don't have a theory of their own. And so all they're doing is co-opting or cherry picking here and there, anything that sort of meets the criteria.
Possibly, yeah.
Yeah. Okay, so anything else on the? You're happy with the second premise? Because I want to ask you about the first one. I know that's, you know, not as scientific in this way, but the first premise is everything that begins to exist has a cause, and I want to ask you about the begins to exist part, or rather prior to that, nothing. Can you explain, A, what the theist, as you understand, what the theist version of nothing is, and what the, quote, scientific version of nothing is, and how they differ?
I'm not sure that there is a scientific definition of nothing. I mean, nothing is not something, it's not a term you find in most textbooks. It's just, you don't look up a textbook in physics, see nothing, and gives you a definition.
So when
I don't
Krauss
think
talks about nothing as the absence of space and time, is that just his personal way of labeling that?
So what Krauss is talking about is a model of the universe that was put forward by, well, I mean, I guess there's two versions of this. I mean, but I think the one that would be most relevant here is Alex Vilenkin's model of the early universe. So what happened was, in the early 70s, there was a chap called Edward Tryon, and he suggested that the universe could come from what's called a vacuum fluctuation. So what that means is, in quantum mechanics, particles can sort of pop in and out of existence. They come in pairs and they appear and then they disappear. This is not controversial. This is accepted science. Now, the suggestion was, well, maybe the universe could do the same, but of course, then why isn't it like, well, why doesn't that violate conservation of energy? Well, it might not, because the positive energy of matter can be balanced by the negative energy of gravity. So if they balance out as zero, there's an equation that tells you, so if you have a vacuum fluctuation, how long-lived that fluctuation can be. And it's a very short period of time. And I remember doing a calculation for a particle called a muon, and I had to calculate how long the muon lived for as a vacuum fluctuation, muon and anti-muon, and it was, I can't remember, it was something like 10 to the minus 24 seconds or something. It's 20, I can't remember, something like that. I mean, it's a very short period of time. But that's because, you know, these two energies they're not balancing out to zero. But it could be that the universe, and Krauss sort of argues that the universe does balance out to zero. So it could be a vacuum fluctuation, but then you can ask, well, where does the vacuum come from? It doesn't really explain, you know, where things are coming from here. And that was the criticism leveled at Krauss and there's a philosopher that I have enormous respect for called David Olbers. I think he's one of the top philosophers in the world. And he wrote a criticism of Krauss in the New York Times saying, no, vacuum fluctuations aren't nothing, because a vacuum isn't nothing. But I think this is one part where I sort of disagree with Olbers, because in Vilenkin's model, he goes further. Vilenkin suggests that space and time might fluctuate themselves. So if you treated space-time as quantum mechanical objects, then they would fluctuate. So maybe space-time could fluctuate into existence. And that would not be a fluctuation from the vacuum. That would be a fluctuation, if you like, of the vacuum, from a state where there's no space and time. And that's a very radical proposal. You know, there's no space and time, and then space and time fluctuate into existence. It's very hard for us to imagine a state where there's no space or time. But nevertheless, Vilenkin modeled it sort of mathematically, and he said there's some probability for it to happen, and if the probability isn't zero, then, well, it must happen. Now, is that nothing? Well, it's just a word, isn't it? I mean, how do you, it depends how you define it. You could argue there are no things, there's no space and there's no time, so it's nothing. However, you might argue, on the other hand, well, there are still laws of physics. Somehow nothing obeys the laws of physics. The laws of physics, in that sense, will still exist. Maybe you might say, well, those aren't nothing. In which case, it isn't nothing. I mean, what should you call that? I don't know. Should you call it nothing or not? I don't know. So
what's your thought then on the philosophical or the theist version, which is the absence of anything? Why? The question I always ask, maybe you can give me an answer or agree or whatever your view is, why should we take that view seriously? Because there's no evidence that it exists in this
Okay,
universe
I think
or
what you're trying
outside.
to get at, what a lot of theists will say, and maybe I've misinterpreted your question, but what I think you're trying to sort of ask is, how do you respond to theists and say, why is there something rather than nothing? You know, surely that means God must explain that question. Why is there something rather than nothing? Which is, you know, a perennial question in philosophy. So I can only give you my own thoughts on that. I mean, my own thoughts are, first off, we don't observe that nothing anywhere in the universe. We can't. It's forbidden in quantum mechanics. So it's not clear to me that this has to be the default state of existence, that you have to explain why it's not that. But why should it be that? You know, why should that be the default? I mean, you don't ask, well, why isn't the universe a giant orange? Because there's no reason why you think the universe should be a giant orange, right? So why should the universe, or why should nothingness be the default? I mean, people argue that it's the simplest state of existence, but I'm not sure that it is. Because if there was nothing, here's another sort of way my thinking goes on this, is let's suppose that there was just nothing, yeah? Well, why shouldn't something happen? You might say, well, there's nothing to cause it to happen. And that's true, there isn't anything to cause it to happen. But if there's really nothing, there's no laws of cause and effect either. There are no laws. And the reason why you don't think something should happen spontaneously, like a giraffe appearing on your table or something, is because there are laws. But if there was a real philosophical nothing, there wouldn't even be any laws. So if there's no laws, what would prevent something from happening? Well, nothing. So maybe something could happen. I mean, I don't know, this is completely speculative. This is just me speculating about existence. But to me, if there was such a nothing, well, maybe there would then be something, because what would prevent something from happening? There are no laws, right? So maybe the universe is in some sort of Alice in Wonderland state with no laws. One of the things that might happen is laws established. You know, I don't know. I mean, this is completely wild speculation.
Well, I always ask people, you know, why should I take that version of nothing seriously? It's like a...
why should it be the default? That has to be explained. And also, why does God explain it? I mean, I could just say, why God rather than nothing, you know? And then people say God is a necessary being, so you have to decide whether you think those arguments for necessary being are valid or not. I don't. And I don't think most philosophers do either. Most philosophers don't even believe in God. So I don't think those... of course, that doesn't prove that those arguments are wrong, but I personally am not convinced by those necessity arguments. And if you're not convinced by those necessity arguments, which I'm not, then there's no reason why God should be explaining why is there something rather than nothing. Why is there God rather than nothing?
Yeah, because he's necessary, or, you know, that's probably...
Well, as I say, you have to appeal to some necessary being argument, but if those arguments are not valid, then there's no argument.
Or they'll often try the infinite regress. Well, there had to be something in the beginning, and that thing is gone.
But then why not the laws? You know, if there has to be something that's like a brute fact, that just that you can say, okay, look, this needs an explanation, and this and this and this needs an explanation. You go back and back and back, and you could just say there is something, this chain, that doesn't have an explanation, right? But why isn't it the laws? And if you want to argue about necessity, maybe the laws are necessary. Maybe they're just logically that those laws have to exist. And there are some laws that do seem to have logical necessity about them. For example, take the relationship between the frequency of light, okay, and the wavelength. They're inverse, but they have to be inverse. It sort of seems to be a logical necessity. It may well be that, I mean, we don't know whether this is the case, but the laws have to be, and they couldn't be any other way. So, of course, we don't know, but we certainly don't know that there's a God that's necessary. So it may well be that there are just things that are necessary, or maybe are brute facts. But if that's the case, why can't it be the laws of physics? And one advantage of saying it's those rather than God is that we do actually know the laws of physics exist, at least in some sense. Of course, exactly in what sense you can debate. But, you know, there are laws of gravity and electrodynamics and quantum mechanics and so on. So at least we are appealing to things we know exist. And that seems more parsimonious than appealing to things that we don't know exist and potentially conflict with things that we do know, like, you know, minds require some sort of energy source, which, you know, that seems to be what the evidence is pointing to.
Great. Is there any more thoughts on either the Kalam itself or the cosmological arguments in general?
Well, I think I want to talk a little bit more about cause and effect, because the Kalam is often appeals to our intuitive notions of cause and effect. And there's a couple of things to say about that. One is, when we experience these causes in the universe, in our daily lives, our intuitive notions of cause and effect, well, we experience as the causes happening before the effects. Causes happen before effects. But if the universe has a beginning, then space and time, you know, begin at the beginning. There's no before the beginning. And therefore, to me, it's not clear that you can still talk about cause and effect, because you've removed time, you know, you remove space. It's maybe even remove the laws of physics. So if there's no laws of physics, no arrow of time, no space or time, how can you still assert that cause and effect still exist? You know, that seems like a wild assumption to me. I mean, causes happen before effects. So things like you need a bit, like I could just say, look, every cause has a prime moment in time, right? If you want to ask what happened before, what caused World War II, you could say, well, Hitler invaded Poland, that happened beforehand. You wouldn't say Kennedy was assassinated, that caused World War II, because that happened afterwards. Whenever you're looking at a cause, if I said, why am I ill? You know, maybe I ate some bad food, you're looking at something that happened before I got ill. So causes are things that happen beforehand. But if the universe had a beginning, there's no before. So to me, it's not clear you can demand cause and effect must still exist, like everything's normal. You know, things aren't normal at the beginning, right? The beginning is a day without a yesterday, if it happened. Well, that's not normal. You know, that's not something that we have any experience of. And therefore, you don't have the right to demand that causality still exists. And of course, there's other issues about quantum mechanics, and people argue that quantum mechanics is fundamentally, you know, they're acausal, and that's what Vilenkin argues. Vilenkin says quantum mechanics allows a breakdown of cause and effect. And maybe there is such a breakdown of cause and effect. I mean, that's certainly a plausible statement. So I think you're not in a position to demand there must be a cause when there's no space, no time, no laws of physics, no arrow of time. I think that's it's just pure assertion.
Yes, and I think that happens a lot with less sophisticated theists. Is they just appeal to intuition, which is what I see a lot of, and hope that, you know, people are going to just accept that because they don't know.
Yeah, I think it does. I think it does appeal to intuition, and it's a clever debating tactic, because of course you want to have your intuitions affirmed. So good debating strategy. But you know, if you want honest appraisal of the world, I don't see why our intuitions should be valid at the beginning of the universe. You know, they're not valid in many regimes. Relativity shows us in high curvature regimes, they're not valid in high speed, they're not valid in the quantum realm. But why should they be valid at the beginning of the universe? The idea that you can just use your intuition and figure all this out, I think I'm skeptical of that.
Well, I think it's a need to know, you know, just to not know, I think for some people is an incredible sort of burden to
want
have.
to know the answers to these questions, otherwise we wouldn't be interested in these whole debates. You know, none of us would be on this show, we wouldn't be doing these debates and these questions. So one thing I think that the people at both sides of this debate, the theists and the atheists, have in common, you know, we should celebrate that, is we both sort of want to know the answers to these questions.
I think some people do. I think some people think they've already got the answer, and only affirm what they've already.
True.
A comment here is, I know we can't trust our mind when it comes to these concepts meaning the beginning of the universe, or maybe the very fast or very small. But it baffles my mind that anything, laws of physics, space, can exist forever. It just doesn't make sense. And this is actually not from a theist.
Well, I wouldn't say that your mind can't understand it. I would say your intuition is not necessarily to be trusted. The physics at these sorts of scales doesn't follow our intuitions. So yeah, I mean, look, I agree that it baffles the mind to think things can go on forever. But it also baffles my mind that they can be finite. I mean, when I was a kid, my dad used to ask, we'd go on holiday and we'd sit down for dinner, and I used to love it when he'd bring up these sorts of questions. And he would ask us, you know, do you think that the universe is spatially infinite or finite? And it's like, how can it be infinite? That sounds crazy. But then how can it be finite? That also sounds crazy. I mean, to me, actually, both answers sound, they're hard for me to get my head around, either option. And I think, I can't remember, was it Kant who sort of claimed that both answers were absurd, or maybe both were, I can't remember what he did. Someone that knows Kant, or 19th or 18th century philosophy, whenever it was, better than me, you know, will be able to hopefully answer who it was that sort of tried to, I can't remember whether they wanted to disprove both or prove both, one of the two, but I think it was Kant in his critique of pure reason. Not sure.
Yeah, I'm not familiar
with
it.
It's hard to get your mind around this stuff, but why should our mind be able to get around this stuff? There's no reason to expect that we should be able to understand this. I mean, I hope one day we will understand all this, but there's no reason why we should expect that we must be able to.
Yeah, and I think, and I hope that, you know, you and I and other non-believers, generally speaking, will accept whatever's true, whether it's comfortable or not comfortable. Like we were talking about, you know, free will or not free will. There's some, you know, particularly unpleasant outcomes in certain scenarios. And, you know, if truth is important, then we'll accept it, whether we like it or whether it changes our belief or whatever the case is. And I don't see that with certainly some theists. I'm not going to claim that it's all of them.
Well, I think we all have cognitive biases on both sides of this debate. Yeah.
Anything else to say on the Kalam or cosmology? Because otherwise, while we've still got a little bit of time left, I want to chat about...
Yeah, I think that's probably as much as we need to say for the moment. Yeah.
Okay, so if you're listening in the chat, please do ask any more questions about cosmology. We're going to move on to fine-tuning for a period of time. If somebody does want to join the chat, Phil is only going to be until 9 o'clock. He might go on, but I'm respectful of his time. And so if we've both been out today, and, you know, 9 o'clock, if he's tired and he wants to go, that's it. So please put some questions in. If you want to join the chat towards the very end, maybe the last 10 minutes or something, let me know and I'll send you the link. You've got a Facebook friend me and I'll send you the link. I'm not going to post it, otherwise we get spam coming through. So Phil, over to you with the fine-tuning. Maybe you could explain the general fine-tuning argument, and then explain maybe a couple of the theist objections and your own with regards to fine-tuning.
Yeah, sure. So the fine-tuning argument is an argument for God that basically says that it looks like there's constants of nature, so the value of the gravitational constant, or the mass of the proton in relation to the mass of the electron, you know, all these sorts of things. But their values have a particular number, and if they were slightly different, life couldn't exist in the universe. And so so we'll call their fine-tuned. They have to be put at this very delicate point. And people have said, well, therefore, there must be a God who's sort of twiddling the dials, he wants a universe with life in it, so he sort of twiddles the dials and puts them very precisely so that he gets what he wants, you know, a universe with life in it. So that's the argument. Now, first off, as you pointed out, there are a number of theist philosophers that have objected to the use of this argument, and I think it's worth commenting on those, saying what their arguments are, because they're theists, and they're not just sort of average, everyday Joe theists. They're professional philosophers who have said this is a bad argument. So the one that I think has the most powerful response is a guy called Hans Halvorsen. He's a professor of philosophy of physics at Princeton University, and he is a theist. He believes in God, but he doesn't think the fine-tuning argument is a good argument. He doesn't think the Kalam argument is a good argument either, by the way. Why not? Well, what he says is that the fine-tuning argument relies on an assumption that God likes life. He wants life. Now, you can imagine, he gives an analogy. Imagine you have like a big bowl full of little balls, and all of these balls are purple, apart from they're all yellow, right here as an example, and there's one purple ball. Okay, you draw one out of the bowl, and it's the one purple ball. Well, the odds of that are very small because they were mostly yellow. So you could certainly argue that there's an intelligent being that was able to select the purple ball, and that makes sense because he likes the purple ball. He picks the purple ball out of the hat. However, that argument will work for deism, but it doesn't work for theism, because theism is a much stronger claim than deism. So for people that aren't familiar with the difference between deism and theism, deism is the belief that there's a sort of God that sets up the universe and then doesn't interact with it once it's begun. So he winds the clock up and then he walks away. He doesn't listen to prayers. He doesn't care how you live your life. In a way, the deists and the atheists have a lot in common in how they would live their lives. They don't think there's a God watching over them. But the deist thinks that there's a God that started things off. The theist God claim is very different to that. God looks over you, he is judging you, he does miracles, and things like that. But more importantly, for this argument, the theist God is omnipotent, omnipresent, so he has more properties than just an intelligent being that created the universe. In this case, in theism, he is the source of all being. And this is very, very important for Halvorson's argument, because he says for theists, he's the source of all being, which means when you look back at the analogy with the bowl, he's the one that fills the bowl up. Yeah. Now, if he loves purple balls, it's a giant mystery. Why is it that the bowl is filled up with yellow balls? Yeah. He said it should be just as surprising to you. What is the fine-tuning argument? It's the argument that the bowl is mostly yellow balls, and there's one purple ball out of a giant sea of yellow balls. Yeah. But if the God loves purple balls, he is the one that sets the probability for life. In other words, you could say this: the fine-tuning is a statement that the probability of life is low. But what Halvorson says is, if you think it's God that sets the probability, and you think God loves life, then you should expect God to set the probability for life to be high. So the fact that it's low is not supporting the existence of God, and it's just a mystery as to why the probabilities of life are low given God than it is given no God. So therefore, it doesn't support the existence of God, not an omnipotent theist God. And you could, I would sort of make a little bit of extra commentary on that, which is this. Imagine we found the opposite of fine-tuning was true. Imagine any value for the constants of nature would give you life. Yeah. What would the theists say in that scenario? I suspect they would say, oh, what a miracle. It could easily be, that only a small number of constants would give you life. But it turns out, oh, look, you can change it from this to that, you still get life. You can change it from this to that, you still get life. What a miracle. Must be God set it that way because he loves life, and that he sets the probabilities for life, so he set them to be high. So it seems to me then that the fine-tuning is not really a prediction of God theory. It's not a prediction of theism. It's just an observation that's surprising given theism or atheism. And the theists are just sort of giving a after the fact explanation that of course could fit anything because God can do anything and God could prefer anything. So that's Halvorson's critique of the fine-tuning argument. In fact, to do one last analogy, he said, imagine you have some humanities student who's a theist, and she goes to a lecture by a physicist who's going to tell her, we've discovered the probability of life, or a life allowing, permitting universe. What should she expect, given that she's a theist? Should she expect that number to be high or low? But if she thinks God sets that probability, and God loves life, then she should expect it to be high. Therefore, the fact that it's low should be just as surprising to her as the non-believer. So anyway, that's Halvorson's argument. Okay. So there's another argument that's run by Lydia and Tim McGrew, who are also professional philosophers, they're theists, they're not atheists, and they also say we shouldn't use the fine-tuning argument. Their argument is that it doesn't. The problem is it's impossible to define fine-tuning, because the way I understand their argument, and people should look it up and see that I'm expressing these people properly, but this is my understanding. You say, okay, there's some range of values that the constants may take, and the values that give you life is a small proportion of that range, okay? The problem is, where do you cut off that range? In order to calculate probabilities, you have to have a sort of cutoff. So, for example, you roll a die, you can say the probabilities, it could be 1, 2, 3, 4, 5, 6. Yeah, and I'm going to not include 7, 8, 9, 10, 11, because I know that the die has 6 sides. The problem for the constant of nature is you don't know the die has 6 sides. You don't know how many sides it has. Okay, so you can imagine a range of values for constants for anywhere from plus infinity to minus infinity. So therefore, any range of life-permitting values is fine-tuned, because anything is small compared to infinity, right? So you could imagine that the value for some constant could be life-permitting, by, it could be, 10 trillion times bigger than what it is and still be life-permitting. Well, that's still tiny compared to infinity, right? And because you can imagine these values have any number you like, then you can't really say that represents fine-tuning. To put a more technical spin on it, there's no measure over the probability space. You can't define the probability space. So when you roll a die, you can define the probabilities. It's 1 in 6 that you'll get a particular number, right? But of course, turns out, for those that may have played Dungeons and Dragons when they were kids, there are die that actually aren't 6-sided. You can get all kinds of die that have many numbers on them, 20-sided die, all sorts of stuff. So the problem is you don't know what die you're dealing with, and therefore you can't, or the technical term is there's no measure over the probability space. You can't do these probabilities that people are arguing you can do. So that's the McGrew critique. So that's another, well, there's 2 theologians there. They're a married couple, actually, Lydia and Tim McGrew. They're both philosophers. So that's their attack on the fine-tuning argument. The third attack on the fine-tuning argument is from a theologian. This is again from a theist, not from an atheist. Is that the fine-tuning argument undermines the theist response to the problem of evil. Now, you might think at first glance it looks like fine-tuning and the problem of evil are just two separate arguments, nothing to do with each other. They don't bump into each other. And so how can advancing fine-tuning undermine the defense, the theodicies for the problem of evil? But they do, according to Hugh Hudson, who's a theologian. What I think his argument is, if I remember it rightly, is so for fine-tuning, you have to assume that God wants embodied agents, because of course God doesn't need the constants to be any value. He can create life no matter what, right? In fact, most theists believe that the creation of life is impossible under naturalism, which to me is telling you, it's just my thoughts now, which to me undermines the fine-tuning, because the whole fine-tuning is, the constants are delicately fine-tuned for life. But of course, if life doesn't come about by natural means, it has to come about by supernatural means, then it's not fine-tuned for life, right? I mean, it's like arguing. Imagine Harry Potter's got his broomstick, yeah? You don't expect him to be tinkering with the aerodynamic design of the broomstick, do you? Because he's using magic to levitate the broom. He's not using aerodynamics to levitate the broomstick, yeah? So it doesn't seem to make sense to argue that God would fine-tune the constants for life, because he's going to use supernatural intervention for that. So you have to make these additional assumptions in order to get the fine-tuning argument to work. You have to assume that God wants embodied agents, because of course he could just create conscious beings in a ethereal plane without any protons or neutrons or electrons or whatever, right? Furthermore, you have to assume he wants sort of a regular, ordered world, obeying laws of physics. So you have to make a lot of assumptions about what the universe would look like if it was made by God. Yeah. And now the problem, how that bumps against the problem of evil, is that a lot of the defenses of the problem of evil is, well, we don't know that this is unnecessary suffering. Yeah. We don't know what the world would look like if God, perfect God, made it. He might have reasons to allow the suffering. But this means that you understand what the world should look like given God, which is exactly what you need. And that's undermining the response. The whole response is, well, we don't know what the world would look like given God, because he may have some reason for the suffering that we don't know. This is called skeptical theism. We don't know what the world would look like given God. But the fine-tuning argument seems to be arguing we do know what the world would look like given God. It would need regularities and laws of physics and embodied agents. So you can see he's basically, I mean, he goes into a lot more depth. And there's a lecture of his online, which you can look up. I think it's Hugh Hudson. He goes into more depth about this, but he's basically saying that the fine-tuning argument is undermining their defense of the problem of evil. So that's that's three theist attacks, if you like, on the fine-tuning argument, where professional theist philosophers have said the fine-tuning argument shouldn't be used by theists. So before I go on to my own thoughts, is it worth, do you have any questions about that or any comments?
Just whether there's an additional one or whether it falls under any of these. The one that obviously I saw with Sean Carroll when he was debating William Lane Craig, which was we don't know what life would be like with different constants if they were tweaked, because oftentimes theists go, oh, if you tweak one constant, then it throws life out, but that doesn't mean that you couldn't tweak another one that would keep life. And how do we know what life is? So maybe you can
I think there is something Halverson said that I think may be saying something similar, because he did say you don't have a measure over the probability space, which of course the McGrew argument is something like that. But in other words, what you would have to do to really do fine-tuning properly, you'd have to be able to compute every single combination of every possible constant and then work out, okay, these are the ones that have life and this are the ones that don't. And the ones that don't are large. But you can't do that, right? You can't compute every possible combination of the constants. So I think, now, I mean, I think that's a general point that people have made. I don't know if that's specific to particular theists, because here we were just covering what certain theists were saying was wrong with the fine-tuning argument. But this is a more general point. I mean, I think there's a more general point here, which is, do we know that, I mean, people talk about the fact of fine-tuning and the data of fine-tuning. And to me, there's no facts here and there's no data here. There are pen and pencil calculations, if you like, or computer models or whatever, that tell you, if you change that constant, life can't be possible. But we can't check that with an experiment. And to me, it's a fundamental principle in science that we don't call things facts that we can't check with experiments. And you can't do an experiment where you change the constants of nature and then see if life still exists. I mean, that's not an experiment you can do. Now, people have made plausible arguments that if you change this, life can't happen. But then other people have actually, if you look at the literature on this, there are people saying, actually, maybe you can change this. So there's a paper that's saying you could switch off the weak force entirely. You could set it to 0 and life would still be possible. Other people have said, oh, well, you can't change the strong force by very much, otherwise life can't exist. But there was a team at MIT said, no, actually you can vary it by quite a lot and life would still exist. And so there is a debate here. Now, I do think it's true that there are a lot of prominent cosmologists that have said, yeah, you can't change the constant by very much, but there are others that have said you can. And the point that I think is worth stressing is that there are no experiments that can adjudicate this debate or could confirm this as a fact. And so because there's no experiments, you can't talk about data either. There isn't really any data here. I mean, you could argue maybe the value of the constants is a piece of data, but what would happen if you change them is not something you can observe. And therefore, I think there is reason to doubt whether these constants are fine-tuned or not. Well, I think there's more doubt than theists would say. And in fact, interestingly, when William Lane Craig debated Sean Carroll, he had a list of cosmologists that had said, yeah, fine-tuning is a fact. Well, I looked at that list, and you know, it's extremely dodgy in my opinion. So Roger Penrose is on there. I've discussed this with Roger Penrose, and he doesn't think the constant nature. He says, oh, I don't think we would know what would happen if you change the constant of nature. So that one was wrong. Alan Guth, I've spoken to him personally, and he says, I'm not convinced by most of these fine-tunings. Stephen Weinberg was on that list, said the same thing, you know. So, and furthermore, most of the other cosmologists, you know, are cosmologists that very strongly support a multiverse, you know, which of course those same theists are not very happy about. So there's a huge inconsistency there, and I think that list was extremely dodgy.
Perfect. So you wanted to say a few more of your thoughts, and then
okay. So yeah. So what I think is worth doing is so we talked about, okay, is there fine tuning or not? What are some theist responses? It's worth going over what Craig, who again all the Muslims copy. Well, sorry, I shouldn't say all the Muslims copy. That's not fair. Many Muslim apologists copy. And what he says, okay, so once you've got this fine tuning, there's three possible explanations for it. There's necessity, there's chance, and there's design. And of course, when we say design, he means design by God, right? So, and he rules out necessity. And how does he rule out necessity? And I'm just going to put a light on, so because I'm probably getting quite dark now. So give me 1 sec.
Yeah, go for it. Yeah, go for it. So again, if you're watching, please put any questions in that you have for Phil. He won't be with us probably much longer.
I'll stick around a little bit later because we haven't had any questions. So I'll just finish this.
One of my panelists here that might want to ask a question as well. Go ahead.
Yeah, that's fine. So let me just finish this thought, sure. And then we'll just do questions after that. Okay. So he rules out necessity by appealing. Well, when he did his debate with Sean Carroll, at least, he ruled out necessity by appealing to string theory, because in string theory it's true the constants are not necessary; they can take on any values. But of course, we don't know that string theory is true, and so appealing to string theory is, you know, a bit dodgy to rule out necessity. I mean, if string theory is true, as we currently understand string theory, it does seem to imply that the constants are not necessary; they can take on different values. But then string theory also seems to point to a multiverse. So, you know, that's going to undermine his next response, which is chance. He said, well, the numbers are just too great, so it can't be chance. But of course, if there's a multiverse, then that's not a problem. Now, he rules out a multiverse by appealing to what's called a Boltzmann brain. So, well, we should be, if there was a multiverse, we're more likely to be a Boltzmann brain. But again, I would hope people watch our video with Alan Guth, and he addresses these points. First off, it's not the case that in a multiverse, Boltzmann brains outnumber normal people, because both are infinite. So you have to have some measure over the probability space, and there are ways to do this, and they can give you less Boltzmann brains than normal observers. So that's just not correct. Now, Craig said, oh, well, you have to use some non-standard measure. But Don Page, who's a cosmologist who again is a theist, said, he wrote a letter to Craig saying, no, there isn't a standard measure, and therefore you can't use the Boltzmann brain argument to rule out a multiverse. Furthermore, inflationary cosmology seems to point to a multiverse, and since we do have some evidence for inflation, I think that's, you know, probably the best game in town at the moment. In fact, the Planck satellite, in our film with Alan Guth, we also interviewed a chap called Georges Eustathio. Georges Eustathio was the cosmologist who gave the cosmology results for European Space Agency's Planck satellite. The Planck satellite is a satellite that was launched in, I think it was 2009, and it's made the most accurate maps of the cosmic microwave background to date. By far the most accurate. And that's the oldest light that we can see. For those that aren't familiar with the cosmic microwave background, it's the oldest light that we can see. And what he said was that the data they got back favors models of inflation that are eternal and therefore point to a multiverse. And therefore, there is evidence for a multiverse. Now, I don't want to claim that this evidence is uncontroversial, that it's definitive. It's not. I mean, it's still up in the air, and we don't know if there's a multiverse or not. What's interesting is that many of the critics of the multiverse within cosmology are proposing a cyclic cosmology instead, which of course is still a wild ensemble of some type. So to me, you can't rule out chance and you can't rule out necessity. And lastly, to get to the God explanation, well, an immaterial mind is something that looks inconsistent with the evidence that we have, that we know about minds. What we know about minds is they seem to need brains and they seem to need an energy source. So if you're appealing to things we know about the world, I don't see how you can still maintain that immaterial mind is the best explanation. So to me, that's a poor argument. So that's my thoughts on it.
Great. One question from the chat, and then I'll let a couple of our panelists perhaps ask you a question. Can you ask, Phil, what would conclusively prove the existence of a multiverse?
Well, I think it depends what you mean by conclusively prove. I think there's a number of ways that we can probe this more and more. So first off, the evidence that we have so far backs inflationary cosmology according to NASA's WMAP team, according to European Space Agency's Planck team. It's still a little bit controversial, and there are some alternatives to inflation that I think we can still entertain. So what we could do is try and more probe the early universe and see whether inflation is right or not, because inflation seems to predict a multiverse. And the more confident we become in inflation, the more confident we are in a multiverse, because it seems to be a natural consequence of inflation. So there are, a number of space probes being launched that will get more data on the early universe, and will either, make us more or less confident about whether inflation happened or whether one of the alternatives to inflation, these sort of mostly they're cyclic models, and they're not in all cases, but mostly they're cyclic models, whether they might be able to sort of switch the game around a bit. There are some other more direct probes. So one of the most exciting ones that come along in recent years is that Anthony Aguirre, is a cosmologist we interviewed, suggested that it's possible that in our past, if there was another bubble universe, it might have collided with ours. And that would leave a signature in the cosmic microwave background. And at first, it looked like we'd maybe seen that. There were 4 signatures that looked like they were bubble collisions. But when, as it was probed more in detail, the confidence level that they were the result of bubble collisions was only 95% confident, which is nowhere near high enough to say that's significant. Interestingly, I think Bill Craig says, "Oh, I only need more than 50%." So he should maybe be convinced they are bubble collisions. But most scientists would then say that's way too low, and that's likely to be noise. There is more data to come, and maybe we could see something like that. More recently, and this is featured in our film, and Alan Guth talked about this, there's been the possibility that maybe during our period of inflation, there was bubbles formed in our period of inflation, and they would look to us like black holes. And this could maybe be the explanation for why there are these supermassive black holes in all the centers of galaxies. And in order to get that, to be convincing, they're working on, the statistics of these supermassive black holes and see if they can predict some properties that maybe we could check with an experiment. So that would be another way to do it. Another prediction that you could argue already is evidence for a multiverse is back in I think it was 87 or 88, about 10 years prior to the discovery of the accelerated expansion of the universe. Steven Weinberg used the multiverse to predict that we should see an accelerated expansion of the universe. That there should be a small value for the cosmological constant. He basically used this argument. He said, well, the value for the cosmological constant, if there's life, it doesn't need to be 0. It just needs to be not too high and not too low. So we should observe a small value, because that's where the statistics would sort of imply the peak is for what we can observe. And so he predicted that there should be, if there's a multiverse, a small positive cosmological constant. And that's exactly what we found. Now, of course, you can argue as to how firm that prediction was and how we should interpret that. And of course, I think if you're going to be really confident in something, we want multiple lines of evidence. So, I think we keep probing the early universe. Of course, it's also possible that possibly Inflation did happen, but maybe it's not eternal. Maybe it doesn't lead to a multiverse. Maybe we've misunderstood it. And maybe as we understand quantum gravity more, we'll understand that, and maybe that can help us sort of understand whether we've understood inflation correctly. But what Guth says is that inflation is generically eternal. If in the presence of inflation, you will get a multiverse. And it's very, very hard to construct a model of inflation that doesn't give you a multiverse. And those ones that do exist look very, very contrived.
Brilliant. We're getting obviously close to 9, and I know I don't want to keep you for hours longer. Thank you very much for staying on a little while. I want to ask the panelists, Raven, you were on first. Is there any questions that you, just unmute yourself, and if there's any questions you'd like to ask Phil, then while we've got him, go ahead and do that.
You know, every time I have a question, he just answers it, and it gives me 10 more questions. I need to like kidnap him for a week. Yeah, so I mean, honestly, I have so many questions, but I know you haven't got much time. So one of the things I was wondering is when you were talking about like the expansion of the universe and the curvature of the universe, is that like an actual thing, or is it an allegory for us to understand? You know, like the tree of life with evolution. It's not an actual tree; it's just a way of understanding.
Well, no, I think it's. I mean, it depends what you mean by actual thing. I think
it's like, is it an actual curve that we can measure? Is like, we look at it and see it's actually a curve?
I think, you can unpack what you mean by actual, but I think the short answer is yes, because what happens is, according to relativity, mass deforms the fabric of space-time and curves it, and that is why you have gravity, because what Einstein tells you is that everything is trying to follow a straight line. But it's following a straight line in curved space-time. The straight line in curved space-time is called a geodesic. And so this curvature is something that's very real. It's what causes gravity. Furthermore, you can measure, this isn't something hypothetical, you can measure the curvature of space-time, of the universe, or the observable universe. And this is, the way you measure it is basically, you basically say, okay, if the universe is flat, then the angles of triangles should add up to 180 degrees. So you just need to look at a really big triangle and add up the angles. You do that. Well, you look at the very oldest light that you can see, which is the cosmic microwave background. And if you look at that line, if it's flat, that will give you a certain relationship between the hot and the cold spots and how big they are. And what we find is that that relationship of being flat is what we see. So the universe looks flat, and it's a very definite measurement. So to answer,
like, doesn't it mean that you'd have to actually have something else to measure it by? I mean, like the only way to measure infinity, I would imagine, is with another infinity, which would mean that you have different types and sizes of infinity.
Well, in mathematics, there are different types of sizes of infinity, but I don't think that's relevant to this question here, because we're only measuring what we can observe. And of course, we can't observe, we can't say the universe is infinite by our observations. We can only say, what we can do with respect to infinity is we can rule out a finite universe of a certain size. So if the universe was finite and small enough, then we could measure the curvature, and because it would wrap round itself, as it were. So if you imagine you're on the Earth, it's possible to measure the curvature of the Earth and see that it has a finite size. But of course, only if you have a good enough measuring instrument, as it were, you can see it from a certain perspective. What we measure for the universe, the only thing we can do is look at the cosmic microwave background, and that's as far back as we can look. And that basically says the universe is flat, which is consistent with it being infinite. However, we can't say that it definitely is infinite, because it could be that the curvature is there, but you just can't see it. It's just too far away. So in other words, imagine the Earth. If you were out in a space station, you could see the curvature of the Earth. You have to go to a certain height to be able to see the curvature. Standing on the top of the Shard in London, or the Burj Al Arab in Dubai.
In a hot air balloon one, I did get to a certain height and I saw the curve of the Earth.
We have to go to a certain height to see the curvature of the Earth, and you certainly can't do it from a low height. So in a sense, maybe that's analogous to what we have with the universe. we've measured as far as we can and we don't see any curvature. So that would imply the universe is either finite, it's either infinite, or it's finite but so big that we can't, the curvature is just beyond our horizon, as it were.
When you actually talk about it being infinite, I mean, like, one of the things that I was thinking of, do you actually subscribe to the idea that energy is eternal? Can't be created, can't be destroyed?
Well, that's a good question. Locally, there's something called the conservation of energy, which means energy cannot be created or destroyed. But in general relativity, things get more complicated because globally, it's hard to define the energy of the universe. And so it's not clear at all that conservation actually applies in general relativity. So, for example, you look at the cosmic microwave background, that's losing energy over time. And that looks like a violation of energy conservation. So it may well be that energy is not conserved in general relativity. But there are a lot of subtleties and arguments about how to define energy. Some people say, yes, it is still conserved, but you just have to define it in the right way. So there's a lot of arguments about that. I think it's certainly, I think we don't know, is the short answer. And it's certainly possible that energy, you're right, cannot be created and destroyed, it's eternal. But it might not be the case. And I don't think we are able to answer that with a definitive answer at the moment.
Yeah, because like one of the arguments I make when I talk about these is it just seemed very simple to me that people talk about the start of the universe, singularity that did this or that, but, you know, if that energy was there beforehand, then that would have mean that, you know, the idea of actually talking about the universe having a start is just ludicrous. So it wouldn't be that the universe started, it just meant the universe had always been there, but the universe as we experience it now, let's just, for the sake of argument, call it the post-Big Bang universe. It's simply different form than the post-Big Bang universe.
Well, it's certainly conceivable that what you're saying is correct, but I don't think we know it to be correct. And energy conservation, which I think that argument that you're making may rely upon, is a tricky issue in general relativity, and I don't think there's an agreed way to how to define it. There's a very good blog post by Sean Carroll about this topic, and I recommend you Google energy conservation Sean Carroll and read his blog post about it, and that will be a bit more detail. But I think the short answer is we're not sure whether energy is conserved in the universe or not.
I'm not sure if that answers the question I had or not. I don't know whether to skip it. I'll just ask it anyway. So sorry if I sound like a 5-year-old. I'm gonna have to watch this episode so many times. One of the things I was kind of wondering is I remember when I was sort of looking this up, and there was this idea that if the universe is finite, I mean, it might not be finite, but different things could happen. Like it could be the big crunch, like it collapses under its own gravity. It could be this, could be that. And it was sort of brought to mind just earlier when you mentioned the idea of two universes colliding. And I was just wondering if there's any, like actually realistically, any models that hold up with the idea that the death of the universe gives birth to the universe. You know, the energy from, like, the energy that happens if it just collapse or snap back might actually,
I think the short answer is yes,
might actually be the Big Bang. So, like, the universe sort of like existing in a different line of them.
There are models like that. I think that's definitely true. I mean, there's something been promoted by, well, two of the biggest critics of inflationary cosmology are Paul Steinhardt and Notorok, and they've proposed something they call the Higgs bang. And what the suggestion is that the vacuum energy, so the energy in empty space, can change. And if it were to change, measurements of the Higgs field show that it's actually not entirely stable, so it could change, and that would actually create a sort of a new Big Bang as it changed, as it underwent that transition. So there are models like that, but we don't know that if they're right or not. It's speculative.
That is so.
I think they're feasible models, and certainly it's possible. We don't know whether they are correct or not.
A question from the chat. Can we see beyond the cosmic microwave background is the limitation due to our measurement instrument, or is it just not possible even with some future device?
I think it depends what you mean by see. It is possible to probe beyond the cosmic microwave background, but not with light. So this is fundamental, and it doesn't matter how good your telescope is, you cannot build a telescope that will collect light older than the cosmic microwave background. And the reason for that is because the universe before the cosmic microwave background was emitted is what we call an opaque plasma. So in plain English, it means you can't see through it. So think of the surface of the sun. You can get a telescope and look at the surface of the sun. You cannot get a telescope and look at the core of the sun, not in light anyway. But there are other things other than light that you might be able to probe earlier. So you could see back earlier. And there are two possibilities there. One is something called neutrinos. And these are particles that very weakly interact with anything. I mean, there are probably trillions of neutrinos going through your body right now, and you don't even notice them. They don't interact with you at all. But because they interact so weakly, that's a good thing and a bad thing. It's a good thing because it means it will be able to give us a signal from before when the cosmic microwave background was emitted, which was 380,000 years after the Big Bang. In fact, the neutrinos would be emitted 1 second after the Big Bang. So you could probe way earlier than the cosmic microwave background. But it's because they interact so weakly that you could do this. But that also makes them really difficult to detect because they interact so weakly. How are you going to find them? I mean, it's hard enough to find neutrinos from the sun, let alone, from this early universe cosmology. But it's not impossible, and people are starting to think about maybe we can do this. Going back even earlier than that, gravitational waves could be emitted from the Big Bang itself, or even before the Big Bang. And it's possible you could detect that and therefore see all the way right back to the Big Bang. That is very, very, very difficult to do because, again, gravitational waves are so weakly interacting. That's what allows you to see back that far because they don't interact with the light that's blocking it, or the sort of fog that's blocking it. But again, because they're so weakly interacting, yes, that means we can probe earlier, but it means they're incredibly difficult to detect. And people are starting to think about how we might detect this, and there are very ambitious plans for spacecraft. You'd need like maybe 12 spacecraft with lasers going between them. There's something called the Big Bang Observer, which is there is an indirect way of probing these gravitational waves, and that's looking at the polarization of the cosmic microwave background. And if you could do that, that's a sort of indirect method of probing earlier periods and detecting these gravitational waves, but it's more indirect. There was a suggestion a few years ago from a team at the South Pole called BICEP2 that they had detected this polarization. Unfortunately, it seemed like probably they just detected dust in the Milky Way galaxy. It's very difficult. These things are very difficult to do, but people are working on it. So with light, no, you cannot see earlier than the cosmic microwave background. But with other things, neutrinos, gravitational waves, it is possible to probe earlier.
Great. One more question from the chat. How might the universe end?
That's a good question. So at the moment, it looks like the universe will just expand on and on forever and ever and ever. However, that depends on, so what has been discovered is the universe is accelerating in its expansion. So if that's caused by what we call a cosmological constant, then it will just keep on expanding forever into the future. Now, of course, what will happen in the very far future depends on some different ideas. So as we've talked about, Penrose's conformal cyclic cosmology requires it to continue expanding, and then it rescales and becomes a new Big Bang. So that's one idea. Another idea is that maybe the cosmological constant is not a constant. Maybe it changes over time, in which case maybe it could recollapse because maybe the value changes. We haven't seen any evidence for it changing, but it's not impossible. And we know very little about dark energy. So I think it's premature to say we know for sure that it's going to continue to expand. But I think the evidence at the moment is looking in that direction. There are some other ideas that, in fact, if you wait long enough, you'll get a new period of inflation, a new universe is being born. There's other ideas that if you wait long enough, bits of space could tear off and create new universes. These are obviously quite speculative, and we don't know. All we can do is sort of take measurements, and at the moment, the idea of it's sort of continually to expand is supported by the data, but people are looking at, you know, more detailed analysis, and who knows what we will find.
Well, just quickly on that one is, if the laws of if the universe is expanding, there's things that we don't know. A question is, why should we put faith into the laws of physics if they, you know, are they universally applicable? If we don't know so much, could they change?
That's a very good question. It depends exactly what you mean by the laws of physics. Like, for example, we've mentioned something like the law of gravity. You have an equation, right, that gives you the law of gravity. And in that equation, there's a value for the gravitational constant. Now, let's suppose the value of the constant changed from plus to negative or something. Yeah, is that a different law, or is that the same law with a different constant? I mean, to some extent, there's a semantic issue there. There certainly have been, believe it or not, there's been measurements that suggest that the constants of nature can actually change in their values, and do change in their values. So one measurement is something called the fine structure constant, or alpha. And there have been a number of teams that have suggested that this constant actually changes over time. Now, this measurement is very, very difficult to do. And we're talking teeny, tiny values, changes in the values. And, you know, there's a lot of controversy about whether this is a real measurement or whether it's just statistical noise. Hopefully in the future, we'll be more confident as to this. There are other theories of the early universe that allow for the constants to vary. So, for example, we've talked about inflationary cosmology, and in different pocket universes in inflation, the constants vary, but the underlying laws are kind of the same, but the values of the constants change. There's an alternative to inflation, which is called variable speed of light theory. And there they explain some of the mysteries of the Big Bang, not by having a very rapid period of expansion, but via an increase in the value of the speed of light. And there's a theory of quantum gravity called Ajava-Lifshitz gravity, which again predicts that the speed of light changes. Now, are these changes in laws, or is it just, these are just changes in values of constants? To say that the actual laws themselves change, there are people who have proposed this. Lee Smolin has proposed something like this. But of course, it's very speculative, and I don't think there's real concrete reasons to think that they could change. But we can't rule it out either. Who knows? You know, that's getting something very speculative. But I don't think we can rule it out. I mean, maybe.
So does that mean that time could be in flux?
Could time be in flux? Well, time is in flux anyway, because different observers see different passages of time. And different locations in different gravitational fields see different passages of time. So time, I think, is already in flux. What's interesting is that a lot of quantum gravity people like Carlo Rovelli, who's worked a lot in loop quantum gravity, have said, and a lot of other people have said, time is not fundamental. What Smolin is arguing, and he's also worked in loop quantum gravity, is that time is fundamental. And what we mean by that is not a question of whether time exists or not, but is it something that's emergent from something else, or is it fundamental? And that's a debate going on. There was a debate at the Perimeter Institute of Theoretical Physics, I think it was this year, or certainly within the last year or so, it was quite recent, about whether time is fundamental. And that's a debate that's ongoing in the community, and we'll wait to see, you know, if that can get anywhere.
So would that mean that now is simply what we experience, but like past and future are happening simultaneously?
Sort of, yeah. I mean, you want to be careful when you use the word simultaneous in relativity, because what's simultaneous?
Well, like is yesterday and tomorrow happening right now as I experience today?
Yeah, but then you say right now. Yeah, only right now is happening right now.
I don't want vocabulary.
Yeah, exactly. What relativity is basically understood to be telling us is that we have people disagree as to what is now. And so you can divide up. So relativity combines space and time together into, if you like, an object called space-time. And people don't agree as to what is space like and what is time like. So if I move very quickly at very high speed, you will see your clock, as you measure my time, as it were, will be different to how I measure my time. So you will see that, you know, maybe I go off at high speed in a rocket, come back, and 100 years might have elapsed to you, but maybe only, you know, 1 year for me. So who's right? Did a 1 year elapse or 100 years elapse? Well, in relativity, there is no right. Both are valid. And in the movie Interstellar, I don't know if you saw that movie, this is something that they confront, because the astronaut in the film, you know, gets his time distorted by strong gravitational fields. And Kip Thorne, who's a very famous cosmologist, was an executive producer on that movie. In fact, he's worked on the gravitational wave detector, LIGO, and he is almost certainly going to get a Nobel Prize in the next year or two, I would have thought. And he worked on that movie, Interstellar. The bottom line is, in relativity, there isn't a definite notion of now. In the same way, there's not a definite notion of here. You know, I live where I live, and to me, that's here. You live where you live, and to you, that's here.
I suppose it's going on about the time being sort of like and we're living frame by frame. But when Interstellar, I sort of imagined, like, if you imagined a stream and you put a leaf on the water, and like the stream is now and the leaf is, sorry, but the stream is time and the leaf is us, and we're sort of flowing down the stream. Then that was sort of what I imagined by Interstellar. Whereas like, I don't know, that seems like, it kind of seems like a different concept of time, but it does.
Okay. So the idea of the stream, you put the leaf in the stream, that's very much our intuitive notion of time, you know. But relativity is understood to be telling us that you can change the speed. You're not fixed at one speed. And so people can be at different locations in the stream and disagree, if you like. They all agree on space-time, but they disagree on what's time and what's space. So what's space like to you could be time like for me. And certainly, and I could say, you know, let's suppose I drop these two objects, right? I drop this one and then I drop this one. Now I think that the bottle was dropped first, and you probably agree with me, right? But in relativity is understood to tell us that there can be other observers that will disagree, and they'll say, no, 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 it was the other way round. And we are not in a position to say they are wrong. They're just in a different frame of reference, and both could be equally valid. And that fundamentally changes the way we think about time.
Phil, that's been brilliant. I realize we've gone over a little bit, and I thank you so much for it. Do you want to just give up
around till 10? Okay, how about that? If you want, I mean, it's up to you.
Wow, I mean, if you're able to, and because I'm sure Raven's got.
So what the hell?
No, Raven's probably got a few more questions for you. I mean, I could ask you. So I'm going to open it up. I mean, if you've got in the chat, and Raven, if you want to ask one or two more, and I'm going to just ask, if you want to ask a couple of other questions. I mean, Phil's specialty is cosmology, but he's fairly familiar with other arguments. I'm not going to put him on the spot necessarily, but you can always get his view. You can always disagree with it. But so if you've got anything else for Phil, he's as I say, knows most of the arguments for and against theism. So I'm going to open it up for the last sort of half an hour or whatever time we have left. Fire away any questions that you have. Raven, go ahead. I'm going to read into the chat, and then I will ask Phil from the chat.
Yeah, so you were going on about earlier, I heard you mention something about the singularity. And like, do you subscribe at all to the theory that the singularity could not help but come because of gravity?
I mean, first, I don't think it's really relevant what I subscribe to. I think it's better to say, right? I think it's better to say, you know, what do most people who study this in depth think? So the singularity looks unavoidable given certain assumptions, but you can always question those assumptions. So, and in fact, that is what has happened in modern cosmology. So the assumption that matter is present in the early universe can be questioned. the assumption that gravity is always attractive seems to be actually false, because inflation and dark energy seem to argue against that. The assumption that general relativity describes gravity in this high energy regime is very dubious. So I don't think the singularity is at all unavoidable. And I say I don't think that. I think most cosmologists don't think that, and that's the more important thing than what I think. So I think that the right statement is the singularity is only unavoidable given certain assumptions, but most cosmologists think those assumptions are not valid.
Okay, I just want to ask you a quick question from the chat. Phil, what's the best theist argument you have come across? Is there anything which has even slightly convinced you, seeing as you're such an open-minded person?
Slightly convinced me. It depends what you mean by theism. So I think, personally, I think deism is more convincing. I think is plausible, because I think what's interesting is that people are showing it might be possible to make a universe in a laboratory, in which case maybe our universe is made in a laboratory. The fact that people have showed it might be possible doesn't mean it actually is possible. I mean, this is very, uncertain science, calculations that are hard to do and have a lot of uncertainty about them. We don't understand quantum gravity properly, so we really don't know if it is possible. But I think that opens up the possibility of deism, but I don't think that supports theism in any way. So if I were a theist and I had to pick an argument, I would pick the fine-tuning argument. It's quite, I think it's the best one they have, but as we've discussed, it's still nowhere near convincing. So if I had to pick one, I'd pick that one. Yeah.
So would you say that the start of the universe, or going back to what I said earlier, the start of the universe in its current form, do you think that was, just in layman's terms, the birth of time?
Was it what, sorry?
In layman's terms, do you think that would be what we might say was the birth of time?
Or was it the birth of time? Well, it might have been, but it might not have been. Certainly, if it was the birth, if the singularity description is right, then it was the birth of time. But most cosmologists don't think the singularity description is correct. So there's some other description, and there are some models where it is the birth of time. So the Vilenkin model, the Hartle-Hawking model, has some suggestion of that, because there's 4 dimensions of space and no dimensions of time, and then time it enters the universe, if you like, when the space dimension gets sufficiently large. So that's a possibility, that's one plausible model of the universe. But there are others that time just, it never gets born, it's always there. So I think at the moment we don't know. It's a possibility, but as we don't know the correct model of the early universe, then we're not able to say that it was the birth of time. It might have been.
I suppose the interesting thing that comes from, I mean, if my understanding is correct, and it probably isn't, but if my understanding is correct, then like if it actually was the birth of time, I'm kind of like, just to go back to your DVD analogy, if there's no time, it's like a DVD on pause. I don't really understand how anything can happen. Where if it's not the birth of time, then I would imagine, just from what I understand, that would actually feed into the multiverse theory, because if that is not the birth of time, then there should be like multiple universes sort of spontaneously happening.
Well, I think the multiple universe idea is sort of, it should be separated from the issue of did time begin, because the multiple universe idea really springs from inflationary cosmology. So if you want to learn a bit more in more detail about this, watch our video on inflationary cosmology. And that springs from just this idea that the universe underwent a very rapid period of expansion. But it turns out that a consequence of this rapid period of expansion seems to be that it gives rise to multiple universes. And that happens at an energy scale that is not at the Big Bang. That's at a much lower energy scale. So then the question is, what happens at the Big Bang? So you can see these are now 2 separate questions. because they're at different energy scales. So what happens at the Big Bang? Was it the birth of time? Well, again, as you say, we don't know. It might have been, it might not have been. But could things happen if there's no time? I used to think nothing can happen if there's no time, because time denotes change. However, I think I've had to revise that view, because it depends on how you define time and what do you mean by time. So, for example, in our last film, Yasunari Nomura, he just said, what is time? It's a correlation between events. So you could have events that don't have any correlation. Then there's still things happening, but there isn't any time. And once a correlation kicks in, then there can be time. So similarly, you could imagine time being defined as an arrow of time from entropy being low to entropy being high. So you could imagine a situation of high entropy or maximum entropy. So imagine a gas in a box. If the gas is perfectly uniform temperature around the box, that's high entropy. It could spontaneously occur that all the particles in the box coalesce, and then it would be low entropy. So imagine that there
wouldn't this be existing in a state of no space-time?
Sorry?
But wouldn't that be existing in a state of no space-time?
I heard the bit about no space-time, but I didn't hear what the question was. Sorry.
But sorry, the analogy you were using as a box, wouldn't like that reality or whatever, wouldn't that be existing in a state of no space and no time?
Well, okay. In this case, I think there would be space, but not time. You can have a description of the universe that has spatial dimensions, but not time dimensions. And that's certainly a description of the universe that is used in some models. So certainly the Hawking-Hartle model has that description.
Fascinating.
So if you imagine this box of particles, and it's in maximum entropy, now the particles are still moving around. So you don't have an arrow of time, because you only define an arrow of time possibly by entropy increasing. But things are still happening. Now, what could happen is they could spontaneously coalesce into a state of low entropy, and then an arrow of time is set, and then they go back to high entropy. So I think it's possible to say that events could happen if there's space but not time. How events would happen when there's no space or time is another issue. But I do think it's at least conceivable that events can happen in a state without time. Certainly the Hartle-Hawking model has that description in it. And cosmologists will talk about something called Euclidean description of the universe, and that's exactly what they mean. There's the 3 space and 1 time dimensions transforms into 4 space dimensions and no time dimension.
Okay. When you say entropy, when you talk about that, how would you define entropy in the way that you're speaking of it?
Well, as we said, there's different ways to sort of define entropy. The loose way to define it, which I think is fine for this purpose, is it's an increasing level of disorder. But as we talked about, a more precise definition is more, at the beginning we talked about microstates versus macrostates, and I think that's a better way to talk about entropy, but they're kind of equivalent anyway. Yeah.
I just want to ask a question from one of our panelists. Oh, sorry, one of our chat folks here. Stars project light. We know there's millions of stars in the universe, so why is the night sky not as bright as the day?
Okay, so this is something called Olbers paradox. Olbers paradox is trying to prove to you that the universe cannot be infinitely big and infinitely old. Okay, it's because of the reason that you just said. If it's infinitely big and infinitely old, the light from the stars would hit you and would prevent the night sky from being black. So there's a couple of things to say about that. First off, it only tells you the universe can't be infinitely big and infinitely old, but it could be one or the other, right? There's no problem with that. So it could be that it's infinitely big but not infinitely old, or it could be that it's infinitely old but not infinitely big. So that doesn't tell you. The Olbers paradox doesn't tell you which. Furthermore, Olbers paradox is not valid in an expanding universe, because let's suppose it's infinitely big and infinitely old. If the universe is expanding, then in a finite moment in time, the universe will become an opaque plasma. And then the light from what's before cannot reach you. Yeah? The only light that can reach you is from when the plasma became unopaque, or transparent. Sorry. So when the photons were released from the plasma, so the only light that can reach you from the past is 380,000 years after the Big Bang. Any light before that can't reach you anymore. So if there were stars in the pre-Big Bang universe, then their light cannot reach you. So Olbers' paradox is, one, not relevant to an expanding universe. It's only relevant to a static universe, as I understand it. And two, even if it was a static universe, it could only tell you that it's not infinitely big and infinitely old, but it could be either one.
One more question here. A couple of times he's asked, what about white holes? Have you heard of white holes?
Yes, I have heard of white holes.
What are they, and are they in any way relevant?
Vague. What's the question? What about them?
He just asked Phil about white holes. It's an interesting topic.
Well, okay, yes, it is an interesting topic, and I think there is something relevant to say about it. The white hole is the reverse of a black hole. So, black holes sort of suck things in, white holes will spew things out. There's something interesting about them, because there's been a discussion recently that if the singularities are replaced by bounces, as happens, for example, in loop quantum gravity and in certain string theory suggestions, and other quantum gravity regimes, then a black hole, when it collapses down to a singularity, there's obviously not going to be a singularity. So it bounces back out straight away. And so black holes basically can't stay intact for very long. They would bounce back out almost instantly, sort of creating like a white hole.
So can black holes be linked to the origin proposed singularity in the Big Bang by the merger or absorption of individual black holes?
Well, I mean, it's possible that if there was a contracting universe before ours, black holes could merge. Yes, but that would then just create a bouncing, expanding universe. It's not really a white hole as such. People are looking at whether black holes bounce out and give us a radiation signal. What's interesting is that the bounce happens very quickly if you're inside the black hole, but it takes a long time if you're outside the black hole. So you'd have to hope that there are sort of primordial black holes, but they're still black holes. But they can bounce back out and so become the reverse. So I don't know if that's something that could be a probe of quantum gravity, and that's very exciting. There's a possibility they've already been detected, because there are things called fast radio bursts, and there's some suggestion that they could be these sort of bouncing black holes, and that would prove, or that would show that singularities are replaced by bounces. But of course, these fast radio bursts, they could have much more sort of ordinary explanations. And in science, I think you always bet on the ordinary explanations, unfortunately. The exciting one tends not to be the right one, but you never know.
Great. One other question here. Are there universes in black holes?
Are there universes inside black holes? Well, some people have suggested that. Lee Smolin has a proposal that when a black hole forms, it bounces back out and creates a new universe. And this is a different solution to the fine-tuning argument, because what he argues is that when the black hole bounces back out, the constant nature changes very subtly. And therefore, there's a sort of natural selection process, because the universe that makes more black holes creates more sort of daughter universes. And therefore, there's a sort of cosmic natural selection, he calls it. And there are other people who have suggested this as well from other perspectives. So there's a guy called Nikodem Popowski who suggested something very similar. And there's been a similar suggestion in string theory. But, you know, it's quite speculative. And I think we don't know. It's not something that we have any evidence for, but it's not something that we've ruled out. And people have made arguments for why it may actually be true, but we certainly aren't in a position to say that it is true.
Okay, I want to just do one quick sort of different one.
Okay.
what is your response to Muslims who say they have, morality based in their God?
Do you mean?
As in, they say they have a foundation for their morality, which is either their Bible or the Quran, which is obviously authored by or inspired by God. And we as non-believers don't have any basis for claiming things are right or wrong.
Right. So basically, this is the moral argument you're basically asking me to respond to.
Yeah.
Personally, I think, but because a God tells you something's right, I don't see why that makes it right. You're just asserting that what God does is right. But that's just an assertion. I have moral instincts that and reasoning that tell me that inform me about what's right and wrong, and that's what I base my morality on. And I think most people have similar moral instincts, and they also have the capacity to reason. So that informs my moral judgments, and that's all I think I need to make moral judgments. I don't see how a God gives you a definitive morality. I mean, who's to say he's not an evil God? I mean, people say, well, God must be good, but that, to me, that's just an assertion. And I don't see any reason to take it seriously.
It's got nothing to do with physics or cosmology.
No, it isn't. No.
It's a stupid question coming from these people, though. If it said in their holy books that their favourite God raped a baby, they'd find a way to justify it.
Well, we were talking about this today. I mean, Abraham, of course, carries out a mock execution of his child. That's torture, is it not? Is that not torturing a child? Most people today, if you kept a prisoner and you carried out a mock execution of that prisoner, that would be classed as torture. I mean, it's psychological torture, it's not physical torture, but it's certainly, extremely harrowing thing to go through. And of course, that's the foundation of, monotheistic religion. So, yes, I agree. They would. It seems there's an interesting study where people were asked to judge a genocidal event, and it was either written in the context of their religion, in which case they thought it was right, or they changed the names and made it like a general of a foreign country, and then they judged it to be wrong. So, what does that tell you? It tells you, yes, I think religion can be used to justify all sorts of.
Well, it's kind of obvious. It's kind of obvious to me that this whole idea of morality is a biological question. What is morality? For one thing, we only find it in social animals. When we think of things like empathy and love, I mean, you can point all over this to the animal kingdom. You could talk about dogs that will run into a burning building to drag out a child or alert their sleeping owners, which goes directly against their self-preservation, or wolves or things. Or actually, have you ever heard of a Judas animal?
A what, sorry?
Judas animal.
I heard animal, but I didn't hear the name of the animal, sorry.
Judas.
Judas, as in?
Judas, as in the character from the Bible.
A Judas animal.
I don't know that term, no.
Well, but this is mostly like, most of the religious people on here are Muslim guests, so just briefly say, I'm sure you know that according to the Bible, Jesus was betrayed and crucified by the Romans. Judas was a follower of Jesus, and he betrayed Jesus to the Romans for 13 pieces of silver. And Judas was so overcome by guilt at his betrayal that he tied a noose around his neck and hung himself from a tree, took his own life out of guilt. Now, a Judas animal, it only happens with social creatures that have to get along, creatures that you would expect to feel loyalty, love, self-sacrifice. Now, what happens is, this is particularly what you do when it comes to pest control and extermination and things like that. Now, you put like a chip, like a tracker, a microchip into the animal, and then you release it into the wild, and it goes and joins up other members of its species, it joins their pack or their group, and then the humans track the Judas animal, and it wipes all these animals out, leaving only the Judas animal to find another group so they can wipe that out. Now, what happens is, by definition, is not a solitary animal. They only exist in groups. But after a certain number of times, it seems to understand it is the one bringing death. So it actually goes against its nature and refuses to interact with any more of its own kind.
Okay, that's interesting. I mean, I'm not familiar with that case, so I can't comment on that. But there's definitely, I think, very strong evidence that there is forms of sort of proto-morality in animals. And
Definitely.
There are cases I'm familiar with. A good example is, rats freeing other rats from, a confined space, and they actually give up rewards and free their compatriots. There's been a lot of interesting study on this, and also animals refusing rewards if they feel they're unjust. So I think there's a lot of evidence for what you might call a sort of more basic notion of morality that exists in.
Also, as I said, it's only you only find these in animals that are social creatures that have to work together. You're never going to get it in a spider. You're never going to get it in a snake. It's only social creatures.
Certainly, it's only been, as far as I'm aware, it's only been seen in social creatures. I don't like to use the word never because sometimes nature surprises us. But I take your point. To my knowledge, it hasn't been observed in non-social animals. But I think, yes, there's a valid point that the existence of proto-morality in animals is a problem for theists. Because, I mean, it's not necessarily disproving deism, but it's certainly something they have to tackle. It doesn't look quite consistent with their worldview that thinks that morality is just given to human beings because we're made in the image of God, and that makes us unique. An evolutionary story of morality does imply that animals may have some sort of proto-morality, and we do observe evidence for that. So I think, I think that it shows that morality is likely coming from evolutionary pressures and not from a divine being.
Okay, I just want to finish it off now with the last question. Thank you, Raven. I want to finish off now with the last question going back to universe. And it's, how much of the universe do you believe is dark matter? This is for you, Phil, obviously from one of our commenters.
Okay. So I want to stress what I believe is completely irrelevant. What scientists have measured is that the best estimate is something like about roughly a quarter of the universe is dark matter. About 4 or 5% is normal matter, and the rest is dark energy. That's our best estimates at the moment. Of course, it's always open to revision. There are some cosmologists, not many, but some that think dark matter doesn't really exist, that we're being tricked and then we have to modify our theories of gravity. I think that is unlikely to be correct, but it's not something that we can definitely rule out. It might end up being correct, but the leading candidate at the moment for the things that we see is roughly a quarter. The Planck satellite gave quite detailed measurements of this. See if I can quickly get the numbers. Planck satellites, dark matter percentage. It's roughly a quarter, thereabouts.
How long ago was this?
Because that came out in 2013, the Planck cosmology results. Let's see. They did change the proportions because we did think it was slightly different. See if I can quickly look it up. So I think, yeah, here we go. So according to Planck, it's 26% dark matter. So I wasn't far off with a quarter. Then it's 5% ordinary matter and 69% dark energy. And that's the current estimates that we have. Okay, all right. Well, thanks a lot.
Absolute pleasure. Your last thing as you leave us, your summary. What would you suggest we as theists say to people who bring forth the Kalam? We're obviously not going to remember all the technical things you've given, but what would you suggest as a response?
So anyone that brings up the Kalam Cosmological Argument, I would say we just don't know whether the premises are true or not. Therefore, you can't arrive at the conclusion. We don't know whether the universe had a beginning. Big Bang cosmology is not telling us the universe has a beginning. It's just telling us that the universe evolved from a hot dense state. It may have a beginning, but we don't know that it did. So you can't say premise 2 is sort of valid. Premise 1, everything begins to exist as a cause. Well, if the universe began, then there wasn't anything before the universe. So we don't have any experience of causes and effects happening without time and space and laws of physics and things like that. So we don't know whether causality will still hold. So I think we don't know whether any of the premises are true. Even if both of them are true, all that's going to do is get you a cause. But is that, I don't see any reason to think, in fact, I see reasons to think why that cause is not an immaterial mind, because, you know, people trying to appeal to the science of cosmology, but the science of neuroscience is implying to me and to many others that minds need physical brains, or at least something physical to get them to work. They also need an energy source to get them to do anything. So disembodied mind looks disfavored by the data. So that doesn't look like a good explanation. Now, an alternative explanation, if there is a beginning and there is a cause, might be something like a proposal like Alex Vilenkin's proposal, where in some sense the laws of physics cause the universe to exist. Maybe they are the uncaused cause. Maybe they are the necessary thing of the universe. You know, the brute, or there could be brute facts. I mean, who knows? The bottom line is the beginning of the universe is a deep mystery, and it's not something we really understand. We can keep pushing back the envelope of our understanding, and it's incredible how far we've been able to push back in our understanding. I think it's absolutely awesome that we've managed to push back and say we can describe the history of the universe for 13.8 billion years. But there's a limit to how much we understand at the moment, and all we can do is try and keep pushing, and maybe we'll get to some ultimate answer, or maybe it's turtles all the way down. We don't know, but we can only keep pushing.
Phil, that's been awesome. Thank you so much for your 3 hours. It's much appreciated. Yeah, I've learned stuff. Hopefully other people have. Take care, and hopefully I'll see you again at some point.
Okay, yeah, definitely. All right, ciao, ciao. Bye-bye.
Yes, Phil.
Come on again. Bye.